I think we'll start. People can join in. Okay. Good morning, everyone. Welcome to the third and last day of online international conference on advances in material science and chemistry 2020. Today we have 6 plenary talks from eminent scientists. We have Professor William D. Jones from University of Rochester, Professor M. Padmanabhan from Amrita Vishwavidyapeetham, Amritapuri. We have Professor V. Suresh from National University, Singapore, Professor Anand Halgeri from PPISR, Bangalore, and Dr. Maya Matthew from CSIR, Pretoria, and Professor P.B. Arvind from University of Groningen. Now, in the post-lunch session, we will have 2 streams of oral presentations. Material science stream will be chaired by Dr. Sudarshan from NCL Pune, and then green chemistry, which will be chaired by Dr. Shivasubramanian from Amrita Vishwavidyapeetham, Coimbatore campus. So let's begin the day with a prayer. I request Meera to sing a prayer song.
ध्यायामो धवलावगुण्ठनवतीं तेजोमयीं नैष्टिकीं स्निग्धापाङ्गविलोकिनीं भगवतीं मन्दस्मित श्रीमुखीं वात्सल्यामृतवर्षिणीं सुमधुरं सङ्कीर्तनालापिनीं श्यामाङ्गीं मधुसिक्तसूक्तिम् अमृतानन्दात्मिकाम् ईश्वरीम् ॐ अमृतेश्वर्यै नमः। ॐ अमृतेश्वर्यै नमः। ॐ अमृतेश्वर्यै नमः। वक्रतुण्डमहाकाय सूर्यकोटिसमप्रभा निर्विघ्नं कुरु मे देव सर्वकार्येषु सर्वदा।
Thank you, Meera, for this soothful prayer song. We'll start with our first talk. We have Professor Jones with us. I request Dr. Zina to introduce Professor Jones.
Inshallah, I hope I'm audible to all. Good morning, all of you. It's a great pleasure for me to introduce Professor William Jones today. Professor William D. Jones is a Charles F. Houghton Professor of Chemistry at the University of Rochester. He obtained a PhD degree in chemistry at Caltech, working with Robert G. Bergman. He moved to University of Wisconsin as a postdoctoral fellow with Professor Chuck Casey, after which he joined University of Rochester as an assistant professor in chemistry. His research interests include organometallic research in strong carbon-halogen bond cleavage reactions, catalysis, model studies, mechanisms, kinetics, thermodynamics, and synthetic applications. He is one of the pioneers in the field of carbon-hydrogen activation chemistry. He has received several awards, to name just a few. He's a recipient of ACS Award in Organometallic Chemistry in 2008. He has also received Arthur C. Cope Scholar Award in 2009, Edward Kirk Curtis Award for Excellence in Undergraduate Teaching in 2009 from the University of Rochester, the Royal Society of Chemistry Organometallic Chemistry Award in 2017, Alexander von Humboldt Senior Research Award in 2018. He has authored numerous research articles along with book chapters. He is a fellow of American Association for Advancement of Sciences, a fellow of American Chemical Society, and he has also served as associate editor for the Journal of American Chemical Society. It's a great honor for us, sir, to have you here along with us during this conference. On behalf of ICAMC team and Amrita Vishwavidyapeetham, let me extend you a warm welcome. Over to you, Professor Johns. Thank you.
Good. Thank you so much for that warm introduction. And it's my pleasure to join this ICAMSC meeting halfway around the world for me. But even though I can't be there in person, at least we can do this electronically. I also want to thank the organizers of the meeting, especially Professor Naveen Kulkarni, who invited me to speak here. We had been talking about this for over a year, thinking maybe I would be there in person, but alas, we have to do it this way. So let me get started by sharing my screen with you, and I'll talk about our work. And just one moment while PowerPoint starts. And Naveen, can you confirm that this is showing well for you?
Yes.
Good. Very good. So the title of the presentation was intended to have people ask questions. Why do weaker bonds lead to more stable complexes? What's going on? Normally, we think of strong bonds in a complex as being a way to stabilize the compound. Yet here I'm going to show you a case where weaker bonds can actually lead to what appear to be more stable compounds. And this is all an outcome of our work in carbon-hydrogen bond activation that we've been doing for a long time in my laboratory. So let's start off with this example from the literature about a reaction on iron where Rieger made this compound on the top left, this iron with this branched alkyl chain attached to it. And what he found was that when this compound was allowed to stand, it would isomerize to the linear isomer quantitatively. So branched, rearranged to linear. And we can understand that because the molecule on the left, the branched carbon center is more sterically crowded, whereas when it rearranges to the molecule on the right, the linear isomer, we now see that that steric interaction is reduced. However, he found in the bottom case, if you put a cyano group in the beta position, the 2 position of the alkyl chain, now the linear form rearranges to the branched form. And that was a surprise, although you can see that that cyano group is polarizing the metal carbon bond, and that appears to be strengthening that bond and shifting the equilibrium towards the more crowded molecule, even though a linear form would be less crowded. So electronics control the bottom reaction, sterics control the top reaction. And this was quite a while ago. You'll notice these papers are about 30 years old. But since then, many other articles appear in the literature that have similar conclusions. Here's another study that Rieger did with palladium. Notice that the branched goes to the linear isomer. However, when you put that cyano group in the 2 position, now the linear goes back to the branched. And again, this is electronics versus sterics playing out. Holland had an example with a phenyl group where he inserted styrene into an iron hydride and obtained the linear isomer as the kinetic product. However, over time, it rearranges to give you the branched species with that phenyl group on the carbon attached to the metal. Again, polarizing that bond, changing the electronics, and making the branched isomer more stable. Consiglio at the bottom inserted styrene into a palladium acyl bond, and what he observes is the 2,1 isomer. That is, the carbon attached to the metal is more sterically crowded with that phenyl group. But again, that can polarize the metal carbon bond and change the thermodynamics of the situation. So these examples have come up over and over again in organometallic chemistry, and it's now pretty well accepted that if you put a group on a carbon attached to the metal, that can change the metal carbon bond strength, and electron withdrawing groups appear to strengthen that bond. So we're going to come back and talk about this again. But first I'm going to talk about the work we've done in my lab that involved carbon-hydrogen bond activation. And I'm going to show you a series of reactions where we activate CH bonds by oxidative addition, and we make these compounds where the metal carbon and the metal hydrogen bond are formed from the hydrocarbon. And notice here I show one hydrocarbon, R1H, eliminating from the metal, and a second hydrocarbon, R2H, oxidatively adds to the metal. And you can imagine that there's an equilibrium for these types of exchanges. And for this equilibrium, there's a driving force that's given by minus RT log of KEQ. Well, if we can measure that driving force, we can realize in the equation down below that it's equal to the relative metal carbon bond strengths, the difference in those two metal carbon bond strengths, and the difference in the CH bond strengths that have to be broken, the R1H and the R2H CH bonds. And in terms of, that's the enthalpy contribution to this reaction. In terms of entropy change, there isn't a big difference on the two sides, except for one important factor, and that is how many hydrogens are available on the hydrocarbon to undergo cleavage. For example, let's suppose on the left we have benzene, R2H, and on the right we have methane, R1H. With benzene, we have 6 CH bonds. With methane, we only have 4 CH bonds. So there's a 6-to-4 preference for the reaction go to the right over to the left, just based on statistics. So that statistical ratio is an entropic factor. And that entropic factor is included in the equation at the end. You'll see this term RT log ratio of the number of hydrogens. And that's how we account for the entropy effect on the equilibrium due to the number of hydrogens that are available. Well, we can rearrange that equation and solve for the relative metal carbon bond strengths. We don't get absolute bond strengths, but we can get relative bond strengths. And that's just equal to the driving force for the reaction that we need to measure experimentally. The difference between the two CH bonds, we know their strengths already. And then this correction factor for the entropy, which we can calculate easily. So that's what we do to learn about bond strengths. The system that I'm going to talk to you about for most of today's talk is this rhodium-based compound that has a tris-perazolyl borate ligand. This capping ligand is very large and bulky. It protects the metal from decomposition and from side reactions, and it allows for some very clean CH bond activation to occur. So our starting material is this carbodiimide complex. It has an isocyanide spectator. The R group here is neopentyl. So it's just an organic, bulky group. And we found that this compound, it's a yellow compound. If you dissolve it in a solvent, shine light on it, it quickly bleaches. In about 15 minutes, it'll go colorless because that carbodiimide ligand is photolabile. It comes off readily. We make a rhodium-1 16 electron intermediate that then undergoes oxidative addition to a CH bond and gives us our rhodium-3 D6 octahedral product. These are 18 electron, they're coordinatively saturated, and they're fairly stable for most derivatives that we've made. Well, here's some reactions with hydrocarbons. If we take the carbodiimide complex and dissolve it in benzene, we find that we get the phenyl hydride cleanly. The starting material is yellow, so if we shine visible light, we will labelize the carbodiimide. When the oxidative addition occurs and we make the rhodium-3 product, the molecule is now colorless. So we don't irradiate the product. We only irradiate the starting precursor. So this allows us to get very high conversions in very short amounts of time. And we found that this reaction is quite ubiquitous with other hydrocarbons. For example, liquid propane activates only the methyl group, so we get only the N-propyl hydride. Pentane gives only the N-pentyl hydride, activating the terminal methyl group. No activation of the CH2 bonds that are weaker than the CH3 bonds by a little bit. However, if we use cyclohexane or cyclopentane as the solvent, now we see activation of CH2 groups because there's no other choice present. So it turns out that in this molecule, after other studies that we did, we discovered that CH2 activations are about 50 to 60 times slower than CH3 activations. So that allows us to get mostly this, almost exclusively the linear product. With mesitylene, we see both benzylic activation and aromatic CH bond activation. And that's a puzzling reaction because the bond strengths of those CH bonds is very, very different. So there must be something going on here that is affecting the stability of these different compounds. Well, let's go and let me tell you how we address the problem of determining bond strengths. We start with the carbodiamide complex, dissolve it in a solvent like benzene, irradiate to make the phenyl hydride, then we remove the benzene solvent and add deuterobenzene in its place. We can now monitor at 25 degrees the rate constant for reductive elimination of C6H6 and formation of the phenylbutyride product. That reaction rate constant can be converted to a barrier height. Delta G double dagger, in this case, is about 31 kcals per mole. We now do the same thing for another substrate, T-butylethylene. Now we make the vinyl hydride, we pump the solvent off, we add deuterobenzene, and we can now measure the rate of reductive elimination of the vinyl hydride. The barrier there is about 27 kcals per mole. And then we do a third experiment. We take a mixture of benzene and T-butylethylene and we irradiate, and what we find is that there's a 10-to-1 preference, kinetic preference, for activating benzene over activating the vinyl CH bond. That delta G, the difference in barrier heights for activating one CH bond versus another, is about 1.4 kcals per mole. So with that information, for these three different kinetic studies, we can produce a picture that looks like this, a relative free energy diagram. On the left, we have the fragment that we generate once we've lost the carbodiamide, that 16 electron rhodium-1 fragment. It can react with benzene, goes over a barrier for oxidative addition, down to make the phenyl hydride product, or it can activate T-butylethylene and go on to make the vinyl hydride product. We know the barriers for reductive elimination from the rate constants. We know the delta G for oxidative addition from the competition experiment. So if we add this number plus this number minus the 26.9, we see that the delta G naught is 5.3 kcals per mole, favoring benzene activation over the activation of the vinylic CH bond. So that's a big driving force, a big difference in energy. The equilibrium constant would probably be about 10,000 for this reaction. In other words, there would only be benzene activation under thermodynamic control. There would be no vinylic activation. So with this method, we went and looked at all those substrates that I talked to you about earlier, the cyclohexane, the cyclopentane, and so on. And what we find is that in competitions from the fastest to the slowest, benzene is the fastest, cyclohexyl is the slowest. They only span about a 1.8 kcal per mole range, or about a 22-to-1 ratio in terms of kinetic selectivity. That's not a very big difference. And if you look at these different substrates, you can see that the ones that are the fastest, benzene and mesitylene, have pi systems. So the metal can interact with a pi system first before it breaks the CH bond. And then the next best substrate is methane, the least sterically congested of the hydrocarbons. And as you go up this list, you'll see that the worst hydrocarbons are cyclohexane and cyclopentane with only CH2 groups. And again, sterically, it's harder for the metal to get in and access those bonds. What we later learned is that there actually is, in the transition state before you break the CH bond, a complex that forms of the CH bond and the metal, an alkane sigma complex. This is a very weak interaction, maybe 5 or 8 kcals per mole, but it's enough to act as a precursor that gives you the kinetic selectivity that we see here. This kinetic selectivity reflects the ability of the metal to bind to the substrate. If we look at the thermodynamics, it's a completely different picture. Because now from the best substrate, benzene, to the worst substrate, cyclopentane, It spans 11.5 kcal per mole range, or 220 million to 1 in terms of the ratio. So a huge difference in thermodynamic driving forces for these reactions. So this kinetic technique that I'm telling you about is nice because we could do it for all of these substrates and get these equilibrium constants, if you like, the driving force for it, that is very, very large. We could never measure these directly. So one way to show this information is to plot it using the relative rhodium-carbon bond strength equation that we developed earlier. We now know the delta G naught, we know the CH bond strengths, and so what we do is relative to benzene, which we call our zero, our rhodium-carbon bond reference. All of the other rhodium-carbon bonds are weaker. They're lower in energy. And if we plot that against the known CH bond strengths, you get a plot that looks like this. It's pretty good line, right? The slope is 1.25. It's greater than 1. And that means that the difference in the y coordinate is 25% bigger than the difference in the x coordinate. So the range of metal carbon bond strengths is 25% bigger than the range of CH bond strengths. And that's what we learned from this study, that metal carbon bond strengths are more important in determining the products. Benzene is the favored product of oxidative addition, yet it has the strongest CH bond. Why is the molecule with the strongest CH bond preferred? It's easy. It makes the strongest metal carbon bond by 25% more than you would have to pay by activating any other bond that may be present. And you can see those selectivities by comparing other pairs within this trend. So we thought we knew everything by the time we had done this study about CH bond strengths or metal carbon bond strengths. And you can see this is back in 1999, so 20 years ago. We thought we were done. But it turns out this is only the beginning of the story. The next substrates that I'd like to tell you about that gave us a lot of insight into the system are the nitriles. So let's take a look at some reactions, in this case with acetonitrile. Very simple, you irradiate the carbodiimide, the ligand falls off, the 16 electron rhodium-1 oxidatively adds the CH bond of acetonitrile, and you cleanly make this product shown in the top right corner, the cyanomethyl hydride. And what we found is that that compound will eliminate acetonitrile in benzene, but you have to heat it up to 100 degrees, and the half-life is 3 days. So it very slowly eliminates acetonitrile. Now compare that to the case where there's no cyano group, the methyl hydride. I showed you that earlier. We could activate methane. And the methyl hydride eliminates methane in only 5 hours at room temperature. Wow. So you replace one hydrogen on the methyl group with a cyano group, and now you have to heat it to 100 degrees for 3 days. That's a huge effect on the stability of the compound. And we said it must be that cyano group polarizing the metal carbon bond and increasing that bond strength. We'll come back to that in a minute. But first, let's look at some other nitriles. The first case at the top is acetonitrile. As I mentioned, we see the cyanomethyl hydride as the major product. The carbodiimide that falls off has a phenyl group in it. And so we can detect traces, maybe 1 or 2% each, of the ortho, meta, and para isomers of CH activation. But those are minor products. If we now go to capronitrile, cyanopentane, we see only activation of the terminal methyl group, the same as what we see with pentane. It's clean. If we do a competition between acetonitrile and cyanopentane, we find that the longer chain molecule wins. The cyanopentyl hydride is formed in a ratio of 2.4 to 1 relative to the cyanomethyl hydride. Now, the explanation we have for that is this metal complex, remember, first binds to a CH bond before it cleaves it. And with the longer chains, the metal could bind to any of the CH bonds. But we know that activation of a CH2 group is slow. It can occur, but it's much slower than a CH3 group. So what the metal appears to do is it migrates from one CH bond to another in a random fashion. And then when it gets to the end where the methyl group is, it inserts quickly. So that's why we only see terminal isomers. It's not that activation of the CH2s is impossible, it's just that it's slow. And by that time, the metal is sorted out where the methyl group is, and it inserts there. So we did another experiment to test this idea. We compared pentane and cyanopentane, 1-to-1 ratio. Let the metal compete for these two substrates. And what we find is that the N-pentyl wins 1.7 to 1 over the cyanopentyl. Why is this if they both have 5 carbons with hydrogens attached where the metal could bind? Well, with cyanopentane, if the metal were to bind to, say, the CH bond next to the cyano group, it would have to migrate 1, 2, 3, 4 times before it could insert into the methyl. And it wouldn't just be a straight walk down the chain, it would be a random walk. And therefore, it would take even longer to get there. In fact, some of the metal would fall off. And in that case, you wouldn't get product. The metal would have to choose over again. With pentane, however, even if the metal binds to the middle CH2, it would only have to migrate once, twice to find a methyl group and quickly insert. So, and it could go in 2 directions. So pentane is favored over the cyanopentane because it's easier for the metal to find that methyl group at the end and then insert quickly. Well, using that data, those experiments, we can compare acetonitrile versus cyanopentane, cyanopentane versus pentane, and then we had already earlier done pentane versus methane. And that'll allow us to compare acetonitrile versus methane, which is replacement of a hydrogen by a cyano group. So here's the picture. In the bottom left, you can see the stable compound, the rhodium cyanomethyl hydride. We have to heat that to 100 degrees to get over this large barrier. We make the rhodium-1 fragment as an intermediate. And now let's activate the methyl of cyanopentane. We go down to here, the cyanopentyl hydride. We know the barriers for elimination for both of those compounds. We know the delta-delta G is very small, 0.5. And therefore, the difference between the cyanomethyl hydride and the cyanopentyl hydride is 8.4 kcals per mole. So a big difference in stability. That alpha cyano group, again, appears to be really important in terms of the thermodynamics of the product. Let's continue by now looking at the competition of cyanopentane and pentane. We know that pentane reacts a little bit faster. The difference in barrier height is about 0.3 kcals per mole. And it comes off a little bit faster than the cyanopentyl derivative. That cyano group is 5 carbons away from the metal, so it doesn't have a big effect on the reductive elimination rate. And that means that these two compounds are at about the same energy. That cyano group is so far away from the metal, it just doesn't perturb the bond strengths. And as I mentioned earlier, we had competed pentane versus methane. We knew that methane was favored kinetically by about 0.3 kcals per mole, and that thermodynamically it's favored by 1.3 kcals per mole. So now with this data, we can do what I mentioned and compare cyanomethyl hydride to methyl hydride. That is shown on this slide. At the bottom, we have the same picture that we were just looking at. I've just added all of the reactants and products. So on the left, let's start with the methane and break the CH bond. That's 105 kcals per mole. We get a methyl radical and a hydrogen radical. On the right side, we'll break the CH bond of acetonitrile. That's 95 kcals per mole. We get a cyanomethyl radical and a hydrogen radical. Now let's break the metal on the left, the metal carbon bond, the rhodium cyanomethyl bond. We get the 4 radicals shown at the top of the slide. And on the right, we'll break the rhodium methyl bond. That'll give us a methyl radical and a rhodium radical. So we get to the same 4 radicals. If we take the numbers that we know, 105, 8.4, 1.3, 94.8, and sum them together, we see that the difference is 3.1 kcals per mole, favoring the methyl over the cyanomethyl. And what we're comparing here is the bond strength, the homolytic bond strength of those rhodium-carbon bonds. The methyl compared to the cyanomethyl, you can see that the cyanomethyl is 3 kcals per mole weaker. The effect of putting that cyano group on the metal wasn't to strengthen the bond. It did the opposite. It weakened the bond. And when we saw this, we were really puzzled because we thought cyano groups made the bond stronger. Everyone did. But here we had evidence, measured experimental evidence, that that bond was actually weaker by 3 kcals per mole. Well, the more we stared at this picture, the more we got to understand what's going on. For example, let's think about this. Let's look at the cyanomethyl rhodium bond. Let's break that bond homolytically. You make a cyanomethyl radical. That radical is resonance stabilized. The radical can delocalize into the triple bond next door. It's a stable radical. When you break the rhodium methyl bond on the right, you now make a methyl radical, one of the least stable radicals. So of course, the rhodium cyanomethyl bond should be weaker. Based on just the physical organic stability of the radicals, we should have predicted that to be true. In both cases, the same rhodium hydride radical is formed. So that is not the origin of the difference in the bond strengths. It's the fact that one radical is resonance stabilized and one is not. All right, so that made sense. The bond is weaker. But notice it's only 3 kcals per mole weaker. Look at the difference in the CH bond strengths. Methane, 105. Acetonitrile, 95. 10 kcals per mole difference. So, and it's the same direction, right? Methane is the stronger bond than acetonitrile. So, yes, the bond is stronger, but it's not as strong as it should be. The cyanomethyl rhodium bond, you might predict, would be 10 kcals per mole weaker than the rhodium methyl bond compared to the known CH bond strengths. But it's only 3 kcals per mole weaker. Therefore, that cyano group is strengthening the bond by about 7 kcals per mole over where you would expect based on CH bond strengths. All right, it's starting to make sense. But then we looked at the bottom part of this picture, and you can see on the left the cyanomethyl hydride compound is thermodynamically much more stable than the methyl hydride. Oh, it looks like by about 7 kcals per mole. Well, wait a minute. Why is that the favored product if the rhodium carbon bond is actually 3 kcals per mole weaker? Why is the molecule with the weaker bond preferred thermodynamically? And the answer to that is to remember back in one of the first slides I show you, when we reductively eliminate one hydrocarbon, we add another hydrocarbon. And there are two components in that reaction. One is the relative metal carbon bond strengths, but the other is the relative CH bond strengths. So on the left, we have methane that we have not activated. On the right, we have acetonitrile that we have not activated, but we've had to break the strong methane CH bond. So what destabilizes the right-hand side relative to the left-hand side isn't the rhodium methyl bond, it's the fact that that cyanomethyl hydride, that bond in acetonitrile, is very weak. And if we break it, we don't pay much penalty, and we leave behind the strong methane CH bond. So the equilibrium is driven to the left in this case, not by the metal carbon bond strength, but by the fact that methane has such a strong CH bond that lowers the energy of that side of the equation. So, all right, we understand the thermodynamics. What about this last sticking point, kinetics? You'll see that the cyanomethyl hydride on the left has the highest barrier for reductive elimination. We had to heat that to 100 degrees for 3 days. That's the half-life. Whereas on the right, the methyl hydride, it comes off at room temperature with a half-life of 5 hours. But wait a minute, the molecule on the left has the weaker metal carbon bond compared to the molecule on the right. Why is the molecule with the weaker metal carbon bond more stable? Why do we have to heat that one up to get it to eliminate? Whereas the methane bond, the methyl bond to rhodium is much stronger. Why does that one come off so easily? Well, if we start on the left with the cyanomethyl hydride, march up this barrier, when we get to the top, what we're doing is to make that acetonitrile CH bond and make that alkane sigma complex. So we make a 95 kcal per mole bond up there, and that lowers the energy of the transition state. However, on the right, when we eliminate methane, the transition state we make is a methane bound to the metal, a methane sigma complex. That CH bond is worth 105 kcals per mole. So we drop that transition state even more. Hence, methane loss is faster than acetonitrile loss. Why? Because when you eliminate methane, you make a strong CH bond. When you eliminate acetonitrile, you make a weak CH bond. So now we understand the kinetics. So amazing. Just studying these nitriles gave us so much insight into the effects of these substituents on metal carbon bond strengths. And it started to make sense. But then we added that point to our graph. And as you can see, it's way off the line. What, 10 kcals per mole away from where it should be. So something funny was going on. And the more we stared at this picture, the more we realized that maybe we shouldn't draw a line through all the data. Maybe we should draw two lines. The line on the right are all hydrocarbons, right? Benzene, vinyl group, methane, pentane, cycloalkanes. Whereas the molecules on the left are all substituted methyl derivatives. Cyanomethyl, or the next one there is the mesitylene. So that's a phenyl attached to a methyl. And then finally, methallyl activates that propenyl CH bond. But again, that CH bond is resonance stabilized by the propyl group. So what we're seeing is maybe these substituted methanes, where the radical is resonance stabilized, have stronger metal carbon bonds. And they're raised up above the trend line that you would expect based on the parent hydrocarbon molecule. Well, is that really true? This was about 10 years ago that we came up with this hypothesis. And so what we did was to go into the laboratory and make more compounds and do more studies. So we could start with any one of these precursors, the pentane derivative, the cyclohexane derivative, or the methane derivative. Allow them to eliminate hydrocarbon at room temperature. The pentyl hydride on the left has a half-life of about 1 hour at room temperature. The cyclohexyl hydride has a half-life of about 10 minutes at room temperature. And the methyl hydride, as I mentioned, has a half-life of about 5 hours at room temperature. But you can dissolve those compounds in any one of these solvents, like trifluoroethane. You make a CF3 methyl derivative. Or fluoromethane. You make a fluoromethyl derivative. Or dimethyl ether. You make a methoxymethyl derivative. And like so on. The difluoro, we get the difluoromethyl. With 2-butyne, we activate the methyl group exclusively. And so we see now an alkyne attached to a methyl. And then in the last case, acetone, we get the enolate, carbon-bound enolate product. So now we have a ketone attached to methyl. So with all of these compounds, we can measure the barriers to reductive elimination, get the barrier height. We can do competitions with benzene to learn the delta-delta G, and we can add those to our picture. Before I show you that, though, I want to point out that we hadn't looked at any sp carbon hydrogen bonds. So I had a visitor from Osaka, Gyeong-shin Choi, who came and looked at terminal alkyne activation. And he found that these work fine. You get cleanly the oxidative addition. And in benzene, you have to heat these up, but they will undergo reductive elimination. And so we looked at the T-butyl, the trimethylsilyl, the CF3, and the hexyl derivatives, all of these alkynes, and measured their barriers and got their data. We also looked at these derivatives, these alkynyl hydrides, where we have a phenyl, a paramethoxyphenyl, and a para-CF3 phenyl. However, here we put the alkyne on with a Grignard reagent and then converted the chloride to the hydride so that we could get these products cleanly and avoid activation of the other CH bonds in the substrate. But again, these will eliminate and we can get the information for those. So here's the way the final picture looks like. And as you can see, there are two parallel lines. One is the hydrocarbons in blue, sp, sp2, sp3. And in red, we have the substituted methanes. A parallel line shifted by about 7 kcals per mole. Those bonds are stronger than they should be. And these are all cases where that cyanomethyl or whatever we're making is resonance stabilized, or in some cases inductively stabilized, such as the case of fluoro or difluoro. And there the bonds are actually stronger than the methyl derivative. Pretty cool. So we did a few more studies. We had this spectator isocyanide, a pi acceptor. We replaced it with a good donor. And let me check the time. I'm almost out of time, so let me move through this quickly. We do the same thing, but now PME3 is the spectator ligand, and do the same kinds of studies. So I'll skip all the details and just show you the plot. It looks very similar. Hydrocarbons, substituted methanes. The difference is that the slope is bigger by about, what, 10 or 15%? So the effect of the donor group is to spread out the range of metal-carbon bond strengths. And then we did this experiment. We put the trimethyl phosphate on. That's in between in donor strength. And when we did that, what we found, same kind of results. Look, two parallel lines, one offset from the other, the substituted methanes. The slope is in between that of what we saw for the other derivatives. So let me finish up. Looking at the time, I'm going to have to end now, I think. Let me just tell you, go back and revisit this question. Remember I told you about the iron hydride and the linear and the branched isomers, and the branched isomer is disfavored over the linear for steric reasons. And the cyano group was preferred on the alpha position because of electronics. Is that right? Is that right? Well, wait a minute. I just showed you that a cyano group on the carbon attached to the metal weakens the bond. If you homolize this bond, you get a radical that's resonance stabilized. If you homolize the primary bond of the species on the right, the linear isomer, you get a primary alkyl radical that's less stable. So why do you favor the molecule that has the weaker metal carbon bond with the cyano derivative? And the answer is, it's because of something we didn't even consider. It's this CH bond that we did not break. So in other words, on the left, we have an extra terminal methyl CH bond that's worth, say, what's a terminal alkyl? Maybe 98, 100 kcals per mole. And on the right, we have this secondary CH bond that's weaker, alpha to a cyano group. It's probably only worth 92 kcals per mole. So it drives the equilibrium, excuse me, what drives the equilibrium to favor the species on the left, the alpha cyano, is this CH bond. That strong CH bond is what drives the reaction. And it's something that was so unimportant we didn't even bother to show it. And it tells us what controls regioselectivity of olefin insertion. For the phenyl derivatives, oops, here they are. Same thing applies. Here's the styrene insertion. The branched is favored over the linear. Is it because the metal carbon bond is strong? No. You homolize that bond and you get a benzylic radical. On the right, the linear isomer, we get a primary alkyl radical. So what favors the one on the left? It's the extra CH bond that you get. So with that, I'm going to have to jump to the end because my time is up and I don't want to run over as the first speaker. Let me just show a picture. Where is it? There it is. Of my group. This is a few years back when Naveen was in Rochester as a postdoc, and we went off climbing on some of the cliffs on the shores of Lake Ontario. Here's Naveen and Miles and some of the other guys in the group that were involved in some of the studies. So with that, I'll thank you for your attention, and I'll be more than happy to answer any questions that you have.
Thank you, Professor Jones, for telling us this interesting story of CH activation. And thank you very much for your time. I know it's the midnight for you. I think we have time for maybe a couple of questions. You can raise your hand if anybody has questions. I think Professor Jones would be happy to answer.
Oops, what did I do?
I think you turned off the video.
There we go.
I
I
think
didn't realize.
somebody,
Any questions?
I see, okay. I'll read out. There is a question from somebody. I have a question regarding the final product formation. Is it only the stabilization energy is deciding the product or any other factor also?
Yeah, that's a good question. So, normally when we started this project, I was trained in organic chemistry mostly, and we think, well, how hard is a CH bond to break? The harder it is to break, then we should get less of that product. That's just the way we normally think about organic chemical reactions. The CH bond, that is the reactant, if you like, controls the reactivity. Benzylic CH bonds are easy to break. Aromatic are hard to break. So that's what we were expecting. When we saw this reversal in trend where phenyl benzene activation was favored over benzylic or some of the other weaker CH bonds, we were puzzled by that. So it turns out that yes, it's the product, the metal carbon bond in the product that really controls the product selectivity. That bond or the range in those bond strengths is greater than the range of the CH bonds in the substrates. And so again, in that term, that equation that I showed you, there were 4 terms, the 2 metal carbon bond strengths and the 2 CH bond strengths. And all 4 of those contribute to the overall stabilization. I think that's what you're referring to, the stabilization energy of the product.
Any other questions? Okay, Professor Jones, I wanted to know, like, if you see in all these the compounds you have used, rhodium is in relatively electron-rich atmosphere because all ligands are kind of more of electron donating. So the metal center is more electron-rich. Do you expect to see the same behavior, or what do you think if you put the rhodium in relatively electron deficient condition?
That's another interesting question, because the other rhodium compounds that have proven to be very useful in CH activation are pentamethyl cyclopentadienyl rhodium derivatives. But the rhodium-3, they're in the higher oxidation state. And they activate CH bonds also, but by a different mechanism. It's more of a deprotonation. So the CH bond comes into the metal, and there's a weak base there to pull off a proton, and the alkyl anion is right there attached to rhodium-3. So it makes the strong metal carbon bond, or depending on the substrate, and then it can be taken off to do more reactivity. But that's all done with rhodium-3, not rhodium-1. And so the mechanism is different. In this case, we start with rhodium-1, and as I said, the CH bond actually makes a complex with the metal. It's very weak, but the metal can then insert into the bond once it's made that sigma complex of the alkane.
Thank you. I think there is one more question. You can actually ask the question is, with cobalt or ruthenium, is it the same?
Yes. For cobalt-1, what I've seen people have studied is the pentamethyl CP cobalt-1, and it does not activate the CH bonds. I think the metal carbon bonds are too weak in that case. However, if you go to iridium, the other direction, down the periodic table, Now the chemistry is very similar to rhodium. In fact, then the bonds are so strong that it's hard to even get them to reductably eliminate. So with iridium, if you activate benzene, you make the phenyl hydride just as we do with rhodium, but now it doesn't come off even at 200 degrees. It's just too stable. With ruthenium, I'm less certain. I don't know of many CH activation reactions with ruthenium, which would be interesting because it's less expensive than rhodium.
Professor Halgeri, you have a
Yes.
question?
Hello. No, it is a good question. I have understood his lecture very well. Okay, thank you.
Okay, I think with this, maybe we can all thank Professor Jones for his interesting lecture.
It's my pleasure. Thank you very much for the invitation.
Thank you very much, sir, for your time. And then in future, we would like to have you in person coming here and delivering a talk. Thank you very much.
One day that would be nice.
You have a good night. So we'll move to the next speaker. We have Professor M. Padmanabhan with us, giving us the second talk. I request Dr. Sarita to introduce Professor Padmanabhan to the audience.
Okay. Am I audible? Am I audible, Naveen?
Yes. Yeah, we can.
Yeah, good morning. It's my pleasure to introduce the honorable speaker of the session, Dr. M. Padmanabhan, to the audience. Dr. M. Padmanabhan currently serves as a professor in the Department of Chemistry, Amrita Vishwavidyapeetham, Amritapuri. He obtained his PhD from IIT Madras in 1977 and did his postdoctoral research at the University of Erlangen, Germany. He was the professor and dean of the Faculty of Sciences, Mahatma Gandhi University. He was also the visiting professor of various prestigious institutes like the Rutgers University, New Jersey, IISER Trivandrum, and IIST Trivandrum. Being an eminent researcher and a dedicated teacher, he has several awards and honors to his credit, which includes the German Research Council Postdoctoral Scholarship and Nature Publishing Group Award. His major research areas include metal organic frameworks, composites, and nanomaterials. He has also published his research in various high-impact international journals. I welcome Professor Padmanabhan to deliver his lecture on the topic Metallogels, a rich source for diverse functional material.
Professor Padmanabhan, can you hear me?
I mean, can you?
Hello?
Can you hear me?
Yes, sir, but it's not clear.
How about now?
It's still faint. It's not loud.
How about now?
Yes, sir, it's better. It's better.
Not so clear. I mean, I know how I want to upload the my.
Yes, sir. You can try.
Can you see my slide?
Yes, sir. I see there.
You can see the slide.
Yeah, if you can please put them on the slideshow.
Slideshow. Is it okay?
Yes, sir.
Oh,
Good to go.
okay. Thank you, Dr. Sarita, for the kind words. First of all, I want to thank our department head, Professor Mangalam, and also other colleagues of mine in the Department of Chemistry for um, assigning me the internal speaker slot to me. And I guess I am the only person from the department who is part of the his main talk. I know there are quite many active people in our faculty members in our department, very active and productive. But I guess it is by virtue of my age that this slot has been allotted to me. And thank you for that. Naveen, is it okay? Am I audible? Hello?
Yes, sir.
Okay,
Yes.
okay. What I want to share with you today is some of the work we have been doing for the last 2-3 years in our department. Most of the work I present here are not published, but however, I will be talking about a few results which we have published some time back in the related area. So before I go further, I just want to thank the people who are involved in this work. Vaishak and Andrews, Alex, they are the main players, and Srina, of course. And Ramesh Chandranath from ISA, who helped me with magnetic studies at a very low temperature. Dr. Sudha helped me with the rheology of some of the gels we generate, and also for some SEM and then temperatures. She has sent to us on some of our compounds. Regarding the outline of my talk, I'll start with some introduction about, of course, gels and metallurgists, because that's the topic. And I also briefly mention about a series of compounds called MOFs, which are nothing but metal organic framework compounds, which are essentially hybrid materials, or you can say coordination polymers. Not too much about these ones because I need to talk about some of the results we had. And since the topic is on metallurgists, and then I need to tell you our chance meeting. In fact, it's a rather serendipitous meeting, or rather finding of some metallurgists. We thought initially it was not useful, but later we could use it for generating several interesting metal organic framework. And then I'll talk about the transformation of these metallurgists. These are metastable metallurgists, and the transformation of these one to a wide variety of crystalline materials, essentially transition metal-based MOFs. Then I'll also talk about lanthanide-based metallurgists, and then generation of several metal cluster and hetero bimetallic MOFs from metallurgists. And importantly for us, at least, we need to separate single crystals out of it, because we need to determine the structure and get to know what the compounds are, what the products are, and for which we have to get the single crystal. So we did a lot of work, or rather, we struggled hard to get some crystals out of every metallurgist and get to know what the compound is, the metallurgy is made of. Or in other words, what are the gelators? And that too in a phase pure form, and also the structure determination. Later, I'll talk about some of the functional properties of these materials we have developed from the metallurgists. I might mention about the unusual magnetic properties of maybe one compound. And catalysis we have done with a metal or gel-derived morph. And a very interesting observation, that is solvent encapsulation properties, remarkable solvent encapsulation properties of some of the uh, gelators. And finally, about light emitting properties of gels and morphs. Light emitting both in the visible range and then also near a region. Well, I need to state what gels are. Most of you know, all of you know, must be, I'm sure. Essentially, I can say that the gels are nothing but three-dimensional supramolecular assembly formed by some molecule, which you call them as gelators, with the bulk solvent or liquid we are using. So in other words, it's a kind of combination of some molecules, you can call it solute or whatever, gelators, interact with solvents and forms a very special state called a gel state. And the gel state is not liquid, it's not solid, it's a state in between. And how does it form? It forms a supramolecular assembly through non-covalent interaction, like hydrogen bonding, essentially hydrogen bonding. Then, of course, we have the other pi-pi interactions and also van der Waals interactions. These are not so very big interactions, but however, actually that contributes to form the supramolecular assembly. And then you have the hydrogels. I'm sure all of you would have heard about hydrogels. And hydrogels are nothing but the gelator, of course, in water, and that forms the gel, and they're called hydrogels. And similarly, you have organogels, essentially made of organic solvents mostly, and then organic compounds. There are also, of course, the inorganic gels. The famous one is the silica gel. And now today I'll talk about metallogels or metal organic gels, in which you have a metal ion and an organic constituent and of course solvents. And they form a kind of supramolecular assembly through non-covalent interactions, mostly hydrogen bonding. Well, there are many applications in gels, and this hydrogels actually keeps the baby comfortable. And you have on the right side, you have another hydrogel, which can be used for wound healing and also as a cosmetic. And NASA has developed an aerogel, actually. It's a very interesting one, actually. It's about 1 milligram the compound. I can see the volume, and it is no solvent. It's actually air is actually in between, actually. And you have in the bottom right, you have the MAC-related gels. MAC is nothing but multiply alkylated cyclopentane. It forms a gel and used as a lubricant in satellites. And of course, we can create gels by using various biomolecules or inorganic molecules, organic molecules, and you can see the fine structure in a TEM fibrous nanofibers. On the left side bottom, you can see, and there's an interesting article, those of you interested actually can read that one. The hydrogels can put stem cells to sleep. That means they can store the stem cell for a long time without any kind of a problem. And such hydrogels are also developed. Now, there are plenty of applications for these gels, and of course, drug delivery, scaffolds, sensors, actuators, and so on. Actually, so many applications. So I need to mention about morph also, because from gel we generate interesting morphs. So I need to talk about morphs maybe briefly. As you all know, morphs are nothing but metal organic framework compounds. When you have a metal ion and an organic linkers, and these linkers should be bifunctional, like a dicarboxylic acid of any type, or it could be a neutral molecule, like two nitrogens on two sides of a kind of a long molecule, which can act as a coordinating atom. Or it could be a carboxylate group, actually, which can coordinate to metal, and then you can have a coordination plus actually the charge. It also provides a negative charge to the metal. And when you react these one in a special condition, of course, they don't interact immediately, and you need to have some special conditions, special in the sense, especially high temperature, and preferably some kind of a pressure. I mean, apply pressure. Normally, people do that in an autoclave, high pressure. But we do all the synthesis in a kind of a very small safety point of view in a glass vial and just seal it and then heat it to a very low temperature. And as you can see that they can assemble together through coordinate bonds. And you can have a three-dimensional structure. And here these are the metals are the nodes. And you have the organic linker actually is the bridging metal atoms and then forming a superstructure. These are not gels and these are crystalline materials. And most by definition, they are crystalline material and that most also demand that they should be also porous. You can understand why they can be porous because you have a kind of a cube here. When they form, the crystals form, there will be some solvent molecules actually to just satisfy the residual valency. But of course, you can heat that one a little bit, maybe at 60 or 80 or below 100 degrees. And you can remove the solvent out. You can have a kind of cavity created. And this cavity can be used. In fact, people have used these cavities for several purposes, storing molecules, even hydrogen storage, important area, or even for separation, gas separation. You have 2 molecules, 3 molecules, and different size, and you can separate gas separation, storage, and you can use it as a kind of a nano cavity where you can carry out the catalysis, nano reactors, and you can also put many other molecules and then activate it or other to do a lot of fluorescence studies. And quite many, actually, there are plenty of applications for this one. What's special about these MOFs are, unlike organic polymers, you know that, carbon, mostly carbon, and unlike those organic polymers, these MOFs have got very unusual properties. As you can guess, MOFs are made up of both metal and then organic. So you have the properties both of metal and also organic components. And with the properties of metal, you know that a metal can act as a catalyst, especially transition metal. And further, actually, the transition metal have got a lot of unpaired electron. It can use it. It can be a very useful. I mean, it can be magnetically interesting. You can do catalysis, and very important about metal actually that metal has got a variable coordination numbers. For example, 6, 5, and you can have 4. 4 can be either tetrahedral or a square planar. So in other words, unlike carbon is actually 4 connected, whereas you have here. You have a metal here. The metal actually, if you extend on the front side, and this is only one cube here, you have actually 6 coordinate means you have one atom in the front also, one group in the front also, which will be connected to another copper or metal atom in the another front. It can form a kind of a 6 connected metal there. So the node can be 6 connected, unlike carbon, and can be 5 connected. It can be 4 connected. And it can be 4 connected, mean can be tetrahedral structure, and then also square planar. So accordingly, the nature of the compound, in other words, the structure of the compound would be so different and variable also. So the coordination number often varies actually. So you can always play with the metal and also ligand. You can have the compound formed in either 5 coordination, sometimes copper especially. 5 coordinated, 6 of course sometimes, and then 4. That variation happens. So you can also play with the coordination number and then change the geometry. So you have a topology, wide variety of topological structure that's possible for the MOFs. And also you have, in addition to the metal properties, you can also organic. Organic can be a fluorescent material. So you have a fluorescent property also attached to the metal. You can also further have a synergistic properties. Both metal and then organic component can show the kind of combined property or rather a synergistic property. Now, there are various MOFs that are reported and then they are used for various functional property. And this is a collage of structures I, of course, collect them here and there. On the left side top, actually, this is a MOF yesterday. I think Professor Boris mentioned about it, actually. Professor Jingley also mentioned, of course, she did not mention much about the MOF, even though she works a lot in the MOFs. And here the MOF 5, actually, it's a metal organic 5. Prepared by famous Yagi, and you have actually here in the top corner here, this is not a single metal. This is a very unusual one. There is an oxygen atom and connected to 4 zinc atoms tetrahedrally, and that forms a node. And as you can see, this is a benzene ring, and benzene ring, they use a dicarboxylic benzene dicarbox, in other words, terphthalic acid, 1,4-dicarboxylic benzene dicarboxylic acid. And in treat with, very easy to make it. And treat with zinc nitrate, of course, solvent is important and condition is important. The only thing you have to add a little bit of hydrogen peroxide, and you can get this product. And what is special about this molecule is what you see as a pink ball is not any kind of an atom. It shows the cavity size. You can see the cavity is so big. And initially, when it formed, the compound is formed, there are solvent molecules into that one. And as I said, actually, you can heat it up a little bit and you can remove the solvent out, and you can have the creatine. Actually, the structure is retained. It will not really kind of tilt this way or that way because rigid bonds, so they'll be intact, but only solvent is removed. So you have a cavity there. You can use the cavity for several purposes. You can do even catalysis within the cavity. 2 small molecules can be put in that one and then do photochemistry, whatnot. Plenty of this. And on the right side bottom, you have another one here. Actually, the right bottom here, similar one. And here you can see that instead of benzene part here, you have a naphthalene here. So nothing about naphthalene dicarboxylate. I think yesterday Professor Boris actually showed the structure actually. So compared to the first one, MOF5, and this is another MOF prepared by Yagi again, you have now the length between this corner and that corner is a little longer than that. In other words, the cavity size of this one is bigger. And of course, you can change this kind of a linker length. You can have more benzene ring attached to it. You can dicarboxylic acid. You can interact with zinc nitrate and hydrogen peroxide, and then you can generate. And there are a series of compounds which are reported with the pore size varying. So plenty of studies have been done on this one. And very an interesting compound on the left side bottom here, I labeled the HKUSD. That's a famous name for that one. Don't worry about the funny synonym they use. It's a Hong Kong University Science and Technology. That's actually, they made this one. And this, I think, 1999, actually, compound is made. You can see the yellow ball, actually. So there were solvents inside. You can remove the solvent out. And you can have a big cavity and you have a smaller cavity. And there are plenty of application for this. So in other words, I mean, I don't want to talk about other things. They are all very exciting molecules, the compounds. Some of them very easy to make it. Some of them, of course, not so easy, very hard also. Well, plenty of applications, I said, for gas absorption and even for gas storage, light emitting purposes, catalysis, photonics, proton conductivity, chemical sensing, drug delivery, whatnot. Plenty of applications, and I will not go. But I really need to mention maybe I think a couple of landmark MOF compounds. As I said, this is the MOF5 which prepared by Yagi. I think it appeared in Nature actually. It's a wonderful paper and exciting molecules. And Yagi did a series of studies on that thing, appeared in Nature Communications, Science, and so on. And I think I don't have those references right here, actually. There's plenty of them. And you can see at the top, these are the Google hits, not, in fact, not citations, over 3 crore, almost 4 crore hits on this one. It's a famous compound, a lot of applications. And as I said, it's very easy to make it, actually. You have the benzene dicarboxyl. Please note that one. You have benzene, you have a COH group on the top and bottom, 1,4 positions. And the metal atom using nitrate, of course, in the solvent they use actually diethyl formamide and probably a little bit of water. You can see the details in the reference here. And there is a little bit of hydrogen peroxide because we have to have and introduce an oxygen here, which is very vital. And this is so-called SBU, structure building block. Instead of metal, we have a cluster of metal, which is a corner. So this one, actually, plenty of application. I will not go into that. And second landmark compound I want to mention, as I said, actually, is the HKUSD1 report by Williams Group in Hong Kong, from Hong Kong. Here they used, instead of the dicarboxylic acid earlier, you have the a tricarboxylic acid at the bottom. You can see the structure. It's a very symmetric one, 1, 3, 5. Benzene tricarboxylic acid. Treat with the copper. It's not zinc, it's a copper. Treat with copper 9, I think it's again DEF, diethyl formamide. And of course, condition little varies, and then heat it up, and then under pressure initially, they got the crystals. And then unlike the MOF5, you can see the a bigger cavity and smaller cavity, and there are plenty of applications using based on the HKUST1. It's a sensor, and as for gas separation and gas separation material, gas storage materials, and many, many of these. We can see so many references on that one. This is the preparation of that. As I said, actually very simple. You take the benzene tricarboxylic copper acetate, and this is DEF, that ideal formamide, if I guess, actually, yes, formate in little water, and treat the copper acetate. And then if you mix them, they are soluble because DEF actually makes it soluble. The BTC is soluble. I call it BTC, benzene tricarboxylic acid. That soluble water DEF mixture and copper acetate. And we do the synthesis at milligram level, not in gram level, very little, and then in the appropriate proportion. And of course, we use a glassware like this, and then heat it up at 90 degrees. And the safety side, actually, we don't heat higher than 100 degrees Celsius because pressure, actually, we don't want to have any kind of problem with that. So we have 90-degree reaction, and then you can get beautiful crystals of it. Actually, this is the HK. You can make this one. Actually, it has been made in our lab. Very easy. You can also do it. Actually, those students, they can easily make the compound and get the crystals of it. And this is the structure I talked about. The bigger cavity here and the smaller cavity here. Okay. Now, having talked about these two landmark compounds, I just want to talk about entry into the MOF. We have been working with MOF compounds, but we accidentally, I should say serendipitously, ended up in getting a metallo gel. As I mentioned, actually, how the HK is made actually is by treating copper salt with benzene tricarboxylic acid. You can easily get it then. So we were trying to make an analogous compound, actually, similar to that one. Whether because HK is so famous can be used, so can we make a similar compound with probably a little different structure? For that, we used another ligand. You can see at the bottom left side. Look at the top and bottom one. So you can see that they look very, very similar, but there, of course, there's a little difference here. In the top, you have a nitro group in the bottom here. You have a nitro group here, not a carboxyl here. This is how carboxyls, that one of the carboxylate group is replaced by nitro group, in other words, 5-nitro isophthalic acid. The isophthalic acid. We call it NEPA, nitro isophthalic acid. So we want actually this being the similar to the BTC, we thought actually, and this is nitro group, and this is similar in kind of disposition overall the atom disposition and the structure, overall structure looks same, but there is a big difference between these two molecules. Even though structure they look same. The top one actually is a tricarboxylic acid. So you have a deprotonation possible at 3 carboxyl groups, and you have a BTC 3- created. And in fact, of course, that would carboxyl group really coordinate from all the 3 sides. Okay. Unlike that one, our NEPA, I call it NEPA, nitroisophthalic acid, only 2 carboxylic acid, other one is a neutral nitro group. So the charge of this one after deprotonation is 2-. The top one is a 3-, and the other one is 2-. So when you make the compound interact with copper, actually, then of course the simple chemistry tells you that you need to have a charge balance. And in the first one, HKUST, the overall composition of the compound actually is Cu3, that means 3 copper, and 2 BTC. It's understood because 3 Cu means 6+ charge, and BTC being 3- charge, and then 2 of them, you have a 6-. So 6- and 6+. But here actually you have a copper, copper is 2+, and the NEPA is actually 2-. But structure is similar. So we thought, okay, we'll try this one and see what happens. So we took 1:1 in the molar ratio, copper 2. Here actually you have to take in the this in the 2:3 ratio. Copper has to be 3, and the BTC has to be 2 equivalent. That's a composition that's a molar ratio you take for the reaction. For here, actually, you take 1 molar copper. Of course, we do at millimole level, copper acetate, and 1 mole of NEPA, because copper is 2+, and the NEPA, of course, the deprotonate will be 2-. So 1 to 1. Very simple. So we took this one, and one thing interesting is that both this copper acetate and the board here, actually, the NEPA, they are also soluble. Copper acetate, little difficulty, and water soluble. This is water, and the NEPA also taken water. Actually, this is also water soluble. Unlike your BTC, you need to have a little bit of DEF. That's why they use DEF in water mixture. And here, the NEPA is soluble in water. So this is a clear water solution, and then NEPA is also water solution. You mix these two, and something happens here. And you mix it, immediately kind of cloudy appearance, like gelatin or something like comes here and stays here. And we thought actually we'll keep it for, we thought actually something will come out actually. For our purpose, it's very important that we get a crystal out of it. Why? Because unlike organic people do synthesis and they get many products, but they have a very easy way to separate them because you can use column chromatography, because you can use the appropriate solvent, make it soluble and run through the column, and you can have separation. You can separate, then take an NMR, and you go to know the structure. You don't have to do anything else. By NMR, you can know the structure of it. But for us, if we don't get a crystal, we cannot actually, no way we can present it. The structure, the composition may be very, very, very simple, but the structure, of course, unless you solve it, crystal structure, you won't be able to know what the compound is. So we waited, and then, several months, and then heated a little bit, nothing happens. Of course, on heating, something happened. I'll tell you what happens. And we didn't get anything. And so we thought of, and this happened sometime back, long back. And we thought of actually, throwing off it. But we kept it for some time and heated up a little bit, about 90 degrees Celsius also. And you can see the whole thing settles then into form a gel. And you can invert that one, keep it like this. And it's a very stable gel. You can store it and save it in this particular form. The entire solvent is encapsulated by the so-called solute molecule you have added, the copper and the NEPA, and that forms a stable gel, very stable. For months together, you can stable it and then keep it like this. Of course, what do we do with this gel? I call this as a metallogel, by the way, because we have a copper in part of that one. Copper, actually. So metallogels are nothing but you have a metal ion and organic component solvent. And you call them as a metallogel. It's a very stable metallogel, but we cannot proceed further unless we know what this material is. It could be a mixture of products, we do not know, and what exactly the structure of the compound. Then only we can do anything about it. We cannot make any guess. You can determine the kind of a composition, but that will not tell you the structure. But luckily for us, actually, in certain conditions, actually, this happened sometime back. Got some crystals of about 20 milligram of actually this one, and you can see that these are all crystals. They don't look so beautiful, but under microscope, you can separate them. You can get a single crystal out of it without any twinning. And once you have that one, you can determine the structure, molecular structure. You can find what the compound is, what the structure is, how it's packed, etc., by single crystal X-ray diffraction technique. And we found out the structure. You can see the structure here. And what you see here is the NEPA part. You have the benzene ring, you have a nitro group popping out. And your carboxyl will be connected to another copper. You just really extend it this side, extend left side, right side, and also front and back. It's a three-dimensional structure. I've taken only one view in one of the axes, and this is the picture we generate from the mercury. And you have a nitro group, etc. What is interesting is that you see the circle here, which I highlighted here, and the blue ones are the metals. You can see one metal, and the metal here is copper. And mind you, we couldn't, this is the ratio is 1:1, one copper actually, and one NEPA. That's the way we mixed it. And so you have to get one copper and one NEPA, and that's the way we got it. But then the structure you can't predict. And then only after seeing the determined structure, we found that this forms a very unusual compound with the green one is a copper. This is a copper one, second copper, third copper, fourth copper, and 5 copper. 5 copper connected together in a very closely. Unlike other morphs, you have a corner and you have the linkers in between. But here, actually, all 5 copper come together, and linked to the other 5 copper like this. through NEPA. Of course, there must be a charge balance here, and so on. And finally, we got the, of course, the composition very simple. Once you saw the structure, we can get to know the composition. It has got, this is a CO5 unit and 4 NEPA unit, only 4, not 5 and 5, 4 NEPA, and you have a 2 OH group to charge compensator. So, mind you, we did not add any alkali, simple water. And we were wondering how actually this is actually OH come from the water actually. So that's a very interesting mechanism. I don't have time to discuss those one. But anyway, only after determining structure, we found that actually it's a 5 copper unit. It's a CO5 cluster, I call it. And this is basically a morph, crystalline material, 3-dimensional nature. And NEPA is the link ligand. In addition, you have an OH minus group, which is coming here and forms a very superstructure, which is like, and there are 11 H2O molecules. Some of them coordinate to the copper, and some of them live in the cavity. So if you now look at the pentacluster on the here, the left side, you can see 1, 2, 3, 4, 5. You can see that. And what is interesting that you have an atom here. This red one is an oxygen atom at the corner. H is the top. H you can't see by single crystal X-ray diffraction because I didn't got 1 electron only, so it's not a good diffracting here. It depends on the number of electrons in the atom, and the hydrogen cannot be easily located. Cannot be located by the single crystal X-ray diffraction. But H is there actually, so here. And this is OH minus here, and you have a 3 lone pairs actually going up here 1 and then 2 and then 3 actually. So through lone pair, this copper is connected through coordination, second copper and third copper. And similarly, you have an OH group here, second OH, because there are 2 OH groups, and this is also one long coordinating to this metal and the second metal and third metal. So we have now beautiful close lying 5 copper in CU5 cluster unit with an OH group actually. So they are close together because OH binds them, brings them together. And in other words, in coordinate chemistry, call it OH minus as a mu3 type ligand, actually. So coordinate to 3 lone pairs to the 3 metal atoms. And then you have the cluster molecule. Okay, having understood this one, actually got this one, got the crystals out of it. And that time I said, actually, we didn't get in large quantities of crystals. Only, I think this overall, the reaction material would be about maybe about 150 milligram. We got only 20 milligram of crystals out of it. The rest of it was powder. But anyway, having understood that this got a CU5 cluster unit, we immediately realized that this could be a very interesting magnetic material because the copper 2 plus is a spin half system, and you have now 1, 2, 3, 4, 5. So something like, kind of an hourglass, something like here. You have 5 copper, and each one is a spin half system. So you have now ferromagnetic and antiferromagnetic. This is, such systems are very interesting, very close lying spin half system with odd number of metal ions. Are interesting system in the terms of spin frustration. For example, the left corner, the corner you can see, you have a 3 spin halves that coming closer together. So this and this can be antiferromagnetically coupled, the spin up, spin down, and this can be spin up. So that is ferromagnetically connected to this one. Ferromagnetic interaction here, antiferromagnetic interaction between this and this antiferromagnetic. And at the same time, you can really say actually this is now actually is ferromagnetic coupled with this copper, and next time it can go to the other one actually, it's antiferromagnetic. So kind of spin switching actually. And it's called spin frustration because this ion is in a frustration whether to partner with this or partner with that one. So that spin frustration is a very important, especially in physics, it's a very important topic, spin frustration. But the energy involved in switching from this to that one is very, very, very small. So to go very low temperature, like 2K, as you can imagine, is the absolute temperature, it will close to 2K or 3K. And then only you can find out the energy involved in this. And so you have the specific measurements. And of course, I didn't have, of course, we don't have any such thing. And thanks to, of course, Professor Ramesh Chandranathan, and I directly was so enthusiastic about a compound because he's a physicist. And then he said, actually, it's difficult to get compound. So asked me, when I was in ICER for, about 5 years back. Not 5 years, 5 years back. So we have a good collaboration actually. So he was interested in compound, and he carried out a kind of I mean, I don't want the time to, these are published results, and I don't time to discuss more about this one. He did a lot of elaborate studies, actually studying from 300K up to 2K, and the measurement takes several days to complete actually. So at various applied field, and then we found a lot of interaction, AF and then antiferromagnetic interaction, and it's a beautiful molecular magnet actually. So in that whole, I don't have time to discuss all that. Very, very interesting observations, of course. Main contributor actually is Ramesh, and then of course the main person is Cyrillin from Germany. He's a theoretician. He did a lot of density calculations to us, and also measurements at a low temperature, I think, with another person at least. And it was probably some time back as a editor's choice. Okay, coming to the same compound, actually having understood this material as a very beautiful, very interesting compound magnetically, I'll talk about other properties of this compound also. So magnetically very interesting. So we thought actually can we make this in large quantity? So we went with the usual one actually in the autoclaves, we call it pressure bombs. And then a large quantity we could make in 10 grams, 100 grams of course we didn't try actually, so 10 grams, even 15 grams can make these compounds. But important thing is that you have to have in phase pure form. That means the compound should be very pure. Otherwise, any magnetic power, any kind of any other phase, any other compound is present, actually that will be you're totally useless. So you have to have a phase pure compound. Anyway, I'll come to that one in a minute. And then we were trying to make a scale up and then try to make it in large quantities. And a very simple reaction, copper is very cheap, and NEPA is also very cheap, and water is a medium. And 90 degrees Celsius for just for 2 days, or even less than 2 days, 1 day plus at least. And pressure reaction. And we could really generate compounds. And you can see on the left side, this is actually produced in one of the reactions. Of course, the condition I don't have this one, the water and pressure, and of course the Auroch heating is also important. What is interesting is that you can see the microsphere actually. They are all uniform size. It's a very simple one. Actually, you adjust temperature, keep it and forget it actually, and then take it out and filter, and then look under this is a microscope picture actually. This is 100 micron size. So you can see that the diameter of these balls or sphere is about 50 milligrams, and it's 50 micron. That means, and you can see all of them are almost uniform. And this is another sample, of course. Also, I mean, I don't have the size here. So it's a bigger one at least. I mean, anyway, so every time actually we are getting a different kind of actually size distribution. Of course, there are a lot of parameters, the solvent volume, and then molar equivalent of the starting materials, and the pressure, and etc. Those ones actually will all tell upon the nature of the product. But all these compounds are, well, have to be pure, and then they have to be what we are looking for. In other words, our CU5 cluster. And how to confirm that one? We cannot take each crystal and then determine structurally. The simple method is that actually we have the crystal, we have structure, solve the structure of the compound from the crystal. We already got the crystal structure of that one. That's a pure. One single crystal means that's a pure one. So we got the structure from that one. So, and as I said, actually we could get only about 20 milligrams of compound out of 150 milligrams. So rest was a powder. So if the rest was not I mean, the material is not the same, then of course there's no point in proceeding further actually, because you cannot use it for any purpose, because the impure sample, there's no way you can separate because they are not soluble, insoluble, there is no way you can separate them out. So it's important that the compound has to be very pure in form. In other words, phase pure form. And how to confirm that one? Very simple. You solve the structure for a crystal, and that's pure one. And this is the bottom one is a simulated structure. Actually, you solve the structure, and you have what is called a crystallography information file, and you can use the Mercury software, and you can simulate it. This is the PXRD of the pure compound, which we can simulate from the crystal structure we have solved for the pure crystal. And we have taken the bulk compound at the top one, the red one, the dried gel. I mean, you don't have to have the crystal out of it. I was telling you 20 milligrams, the rest of it actually is powder. Actually. We take the entire compound and took the PXRD, the entire sample. And look at that, the top and bottom, there's a 1-to-1 correspondence. this and this. Every peak is matching exactly. Of course, intensity also exactly. Of course, intensity generally does not really matter, actually, but of course, intensity also exactly matches exactly. That means it's 100% pure. And as I said, the yield wise is 99%. So in other words, once you solve the structure, you don't have to worry about, you don't have to get crystals out of it. You simply get the powder form, take the PXRD, and the crystallography information file is available in CCDC, Cambridge Crystallography Data. The crystal structure, you can simply write, you can get the zip file and use the Mercury software, which is freely available. And you can generate, simulate the PXRD, and then you just take the PXRD with compound and just match. And if they're matching, that means the compound is pure. If there is no impurity, if there's an impurity, there'll be additional peak here because there's another phase, and there'll be kind of diffraction peaks coming from that one also. So that's a way to, especially for inorganic, this is the way to prove the purity. Unlike organic, of course, you take NMR and then or column chromatography, and you can get the pure product out. Here, there's no way you can separate. Purity can be easily checked by taking a PXRD. PXRD takes only 30 minutes. Well, having talked about the magnetic property of Cu5 cluster, and we realized that copper is in a very unusual oxidation. I mean, I didn't show you the close-up of the copper coordination. As you all know, the copper coordination is varying. Sometimes 4, sometimes 5, square pyramidal, and sometimes octahedral. Of course, you can't tell the distortion, etc. So 6, 5, and 4 at least. So we found some of our copper, actually 5 copper in one unit. Actually, some of them are 4 connected, and some of them 5, and some of them 6, actually variable. So variable. And other one actually is 6 coordination. That means you have 11H2. They are part of actually water molecules are coordinated to copper, and some of the water molecules are lying in the cavity. Okay, and then we realized that actually the copper having variable coordination number, and also the 6 connected or 6 actually there are 2 water molecule coordinates. You can easily remove it by heating it. So in other words, you take them off and there are 11H2, you can do a TG and then find out temperature where the water goes and keep the bulk of the compound, and that temperature probably at 100 or so, or the water molecule will go. And what does it mean? The water will go from the cavity, and water will also go from the coordination site of the copper. So in other words, on heating, what you get actually waterless compound, dehydrated one, and that's a very interesting compound because copper is in a coordinatively unsaturated form. And this is famous for catalysis because catalysis at the metal is done through a kind of a ligation initially, and there's a kind of electron density distribution. That's the way the molecules, small molecules, get activated, and that's the way catalysis is done. So having realized that one, we found that the water can be easily removed. So we thought, why can't we do catalysis? Because we can create a coordinately unsaturated copper, and that too copper is in large excess. 5 copper connected together, there's a synergetic interaction, cooperative interaction possible. So we thought we can use it as a catalyst. And the catalysis we thought of is a simple carbon monoxide, carbon dioxide conversion. Of course, carbon dioxide, people do talk about carbon dioxide. Please think that it's not a toxic one. We, of course, breathe and breathe out carbon dioxide always. Nothing happens to us. But, of course, it's detrimental to, of course, to atmosphere because global warming, etc. But carbon monoxide is really poisonous. And if you look at this motorcycle and look at the thing that's coming out of the engine here, and this engine, the smoke here contains about 30,000 to 100,000 ppm carbon monoxide. Very dangerous. Even up to 100 ppm, at least, if you stay for an hour or so, you'll collapse and finally you might die. Actually. So very, very one. So this one is very important. Actually, people now the government is coming with a lot of regulations actually to control the pollutant here, and with this much contamination in the smoke here, actually, it's important that you have to have the CO removed. Of course, there are also NOx and other things, particulate matter which coming out. They're also dangerous, but carbon monoxide is more dangerous to that. And of course, I mean, normally in all the vehicles, this doesn't happen that way. There is a kind of a catalytic converter there, and where they use platinum and rhodium, very, very costly material. And that's the way whatever the smoke comes out, And there's a less content in content of carbon monoxide in that one, thanks to these catalytic convert, where they use platinum and then rhodium. These are all expensive metals, and that's the way it's converted. So we were thought actually that this is an interesting reaction we can try, whether we can convert the carbon monoxide to carbon dioxide in presence of O2, because especially thinking of this engine, you need to have a little temperature, because engine you have outside here, you have a temperature that will be sufficient. So we can remove the water from our, suppose we use our material inside. At that temperature, water will go off. And if a copper in a coordinatively unsaturated form, and of course air is available, and then CO plus O2 can react together to form the carbon dioxide. Well, of course, CO will coordinate to metal initially. And of course, I don't want to talk about mechanism. So we thought of trying this one, and we did collaborate with a Japanese group, thanks to Jingli. Actually, she has contacts. And then we sent the sample to him, and then he did the measurement. We made this, we sent the sample, and then material powder form. Powder form, of course, we made sure that actually is a pure form by PXRD checking, and then we sent the sample, and then they did actually, they heated the sample, and this reaction, they pack it in a small tube, and then pass carbon monoxide and O2 and heat it up. And you can see that low temperature, room temperature, nothing happens. This is a conversion, y-axis is a conversion of carbon monoxide to carbon dioxide, and no conversion initially, but as you increase the temperature, look at that 100 degree. And the coordinate of water goes from the carbon, that our MOF material, and then you have now the catalysis happening here, conversion happens. At this temperature, complete conversion, 100% conversion of carbon monoxide to carbon dioxide. And you are making a toxic one, converting into carbon dioxide. And he did the trial with repeatedly with 3 times actually with the same sample. Nothing happened, so you can always reproduce the result. So this is one another. I will not. I don't have time to discuss more on this one. This is the 2 applications we got. But the simple. Initially, we got a gel, and from that one gel, we were planning to throw it out, and finally, luckily, we got the crystal. And this is what actually the pace. I mean, very often you have to be looking for, especially for the youngsters. Actually, want to say that whenever you find something unexpected, don't ever throw it out. Actually, there will be something coming, and then look for an unexpected one. Actually, that is where the exciting things would be there. Actually, so that's why we did not really throw out the gel, and then we waited, and we were patient enough and got. Of course, this the story starts from maybe 4 or 5 years back, or even 6 years back. Actually. Got the crystal, and then now it's very easy for us actually, and we simply mix it and we get phase pure form of that. But anyway, now I'll come to our second case, the second case of metallurgy. This is also a serendipitous. I mean, this was not serendipitous because once we got the copper gel, actually we were interested in it whenever we were looking for whether any kind of metallurgy can be formed. And I must say that I accidentally landed up in working with the lanthanide system. Actually. So initially, I am just a transition metal inorganic man. Actually. So I worked on lanthanide because I had a joined student, Vaishak, of course, working on some organic thing for the for photo, some as a kind of sensor, actually, so fluorescence and properties. Actually. So I being part of that one thought actually I should also contribute. So I am a metal man, an organic man. So I thought I can just keep the transition metal, then go into lanthanide. And lanthanide is a very interesting one. Okay, so lanthanide, because they have the f orbital, 7 of them, you have magnetically very, very interesting. So the catalyst. In addition, unlike a transition metal, lanthanides are fluorescence materials. For example, if you take neodymium, it is actually, if you irradiate the UV light, you can have an emission coming in the near area, very sharp emission. And similar to europium, you have irradiated with either visible or UV light, and you have a radiation, not visible, UV light, and you have emission coming in the red region, and ytterbium and terbium in the green region, green to blue region. Sorry. Hello. Hello.
Sir, please continue.
Hello.
Yes, sir. Professor Padmanabhan?
Hello. Am I audible?
Yes, sir. Yes, sir.
Oh, but I think I had a call from you. I thought actually because I have some net issue. No problem, right? I think you only.
No problem, sir. You have maybe two more minutes.
Oh my God! Actually, sorry. I'm so sorry. Actually. Okay, in a lanthanide-based MOF, I don't have time for. I mean, anyway, run through it. So this is another lanthanide-based metallogel, and treat with lanthanide nitrate and then NEPA, and you have a DM of water mixture. And Vaishak did. Am I audible now? Hello.
Yes, sir.
Hello.
Yes, sir.
Okay. Okay.
Yeah, it's clear.
Okay, and of course now we were interested in getting a gel, and then Vaishak did quite a lot of solvent mixture reactions, and then sometimes we get gel, sometimes get crystals out of it, and so on. Actually. So these are metal gels. If you keep it, mix them together, colorless liquid, both not transition metal, lanthanide, and then NEPA. Keep for a long time, nothing happens, but you heat it up, actually you have a gel formation. And this is something like a super gel. I would call it actually super sponge, because we take say small amount 9 milligram, and then we have used 2.5 ml water and 2.5 ml DMF, and this one contains about only 9 milligram of lanthanide. You take a lanthanide nitrate actually equivalent, so it will be 9 milligram. So we can find out actually, so one lanthanum would takes up as much as 4,000 water molecules and 1,000 DMF. I mean, so in other words, it forms a stable gel. Initially is remains a liquid, heat it up at 90 degree, and it's a gel, and then we call it super sponge. Very stable, can keep for days together and months together, nothing happens. The super sponge. So we thought actually these gels and metal gels can be considered like in the system metastable, and here is the gel state 1, and with a little kind of a push, actually some kind of a either solvent variation or kind of heating, we thought actually we can bring that into a very stable one. In other words, convert this gel form to some crystalline material. The first one we were interested in getting to know what gel is made of. We have taken lanthanum nitrate and then NEPA, and what actually this material is actually. So we played with the solvent, and finally we got 3 such compounds actually crystal separated out of that one. The first one is this and this. Actually, this is also a part of that one. And second is a lanthanum with the NEPA here coordinated. And then third structure, third crystal we separated in a different condition. This is in little excess water, and this is little DM of excess. And this is in NaOH condition, the little alkaline condition. So we were able to get 3 different crystals out of the same thing, same gel. Actually. And we this is simulated for the second structure, this compound, and this is simulated from the third compound. Actually. So these are simulated structure. So we took the gel and removed the solvent carefully without heating much, and then took the powder and then took a PXRD of that one, bulk one. As you can see, the PXRD of the zero gel means without any kind of solvent. Take this again. So if you take the 1 and 2, the top and the blue and then pink, and add up that one, you get this one, approximately. So in other words, we know this is nothing but made up of actually this, the second and then third compound. The other one we got in alkaline condition. In other words, the gelatry is nothing but the combination of this and this. So we wanted to see that one under a kind of a SEM. We got SEM one kind of species, and term actually other one actually is the nanofibers like this is the second type of compound. And this is the bordering light microscope image of that one. I will not go into detail that one. But what is interesting is that we got emission characterized. For example, you take this one and keep it in a small, we have a small setup where you can have a, keep the sample and then ready with the UV light, and you can see the blue emission. I hope it's seen. Hello? Hello?
Yes,
Naveen?
sir. You are audible. Yes, sir. Yes,
But
sir. You are audible.
keep getting your call. I mean, probably you're calling me. Actually.
Yes,
Okay.
sir.
Okay. All right. Okay. Oh, sorry. Actually. almost time for me? Oh my God. Okay.
Yes, sir. Yes, sir. You can please go.
UV light. And we also did actually record spectrum. This is excited spectrum and the emission one. And you can see that emission coming in the range. So in other words, this is a fluorescent material which we get on UV radiation. You get a blue light coming from that. We did rheology for to make use of this one for any practical purpose. We want to make them in kind of a wire or something like. So we want to do rheology, and Dr. Sudha helped me with the rheology. I will not go into details. We made a neodymium analog in similar way, and we got an emission, actually UV light giving it, and you have an emission coming in the, you can see the blue one, and that is the near IR region actually. So very sharp emission coming, and on giving UV radiation actually, the NEPA, the organic part, absorbs the radiation, emits in the visible range, that being picked up by the neodymium. This is neodymium, and the neodymium. It's basically energy transfer. UV light absorbed by NEPA and then given to the neodymium, and neodymium is in the near IR region. And we have europium here in this polarizing microscope image. This one I will not go into details, but we did some metallogel. So having got two metallogels, one is copper based in lanthanides, we tried mixing these two in a different way in certain conditions. So this is solid and this is solid. I can take half of it and half of this one and mix, and something happens. You can see immediately whole appearance changes. The gel breaks down. You can see the water, water coming and everything settled the bottom. And you can see something, a blue dot coming here. Within no time, everything transformed into a blue material. This is a crystalline material. And this phenomenon is called Oswald ripening. The whole thing converts into this blue material. All powder goes to one. And this one is quite different from the starting material, starting compound. We got single crystals out of it. We could solve the structure, and we could do the reaction in various conditions, get several such products. I mean, I don't want to have time for those ones. And we did magnetic studies, we could study fluorescence studies, and these are some of the structures we got from. I don't have time. In other words, I was discussing about our encounter with metallurgists and making use of that one and then getting useful out of product out of. In other words, metallurgists can be a rich source of functional materials. And metallurgists can be, of course, I want to thank all the people who are involved in this one. And of course, in a lighter note, I want to say that metallurgists can be considered something like a wheat dough. And whatever she is doing, you know that all of familiar. Making a dough out of it, and you can convert them into wonderful products. So change the condition, or one of them, some of them fry, you can make bread and then kind of pizza or whatever it is. And this is the way you can transform gel, it's in a metastatical state, transform into useful products. So this is an interesting area I thought I could share with especially youngsters, so that I can just caution them that if those who are working with an organic system, if you get some non-crystalline material, don't worry about it. You can play with it and get some useful product and then convert them into. So thank you for your patience, and thank you. I don't think I shot up too much. Thank you, all of you.
Thank you very much, Professor Padmanabhan, for this interesting talk about the metallurgels your group is working on from a while. And also for being a great supporter for all the activities we do as a department. Thank you. I see that we are actually running out of time, and I see Professor Suresh is on board. So I think we will not have Q&A.
I'll take a question from him. Yeah, because.
Yes, sir. So I request participants, if you have any questions, you can actually post it here in the chat section, or
Dr.
you can
Naveen,
email
Dr.
Professor
Naveen, if you don't
Padmanabhan.
mind, can I take the.
Professor Padmanabhan, you were trying to say something. Okay, I think now it's time to go for our next speaker. We have Professor V. Suresh from National University, Singapore. I request Dr. Gopal to give a brief introduction about Professor V. Suresh.
Thank you, Dr. Naveen. Good morning, everyone. It's my pleasure to introduce Professor Suresh Vallavatil, Associate Professor at the Department of Chemistry, National University of Singapore. He graduated BSc and MSc from Calicut University, Kerala, and received his PhD from University of Victoria, British Columbia, Canada in the year 1992. Before joining at the National University of Singapore, he was at Max Planck Institute for Polymer Research, Germany, and Cornell University, New York, USA, as postdoctoral researcher. His research research interests include biomaterials and nanomaterials, especially centered at nanotoxicology, nanomedicine, and multifunctional polymers and developing methods for water purification. He is the recipient of several awards include Outstanding Scientist Award, Faculty of Science, National University of Singapore, and Erudite Professorship at the School of Chemistry, MG University, Kerala. He is a member of editorial board of quite a lot of international journals and published more than 250 research publication papers in the international journals. With this introduction, I welcome Professor Suresh to International Conference on Advances in Material Science and Chemistry and deliver the talk titled Plastics, a Boon or a Curse. Professor Suresh.
Thank you for the introduction. And can you hear me? Are you able to hear me?
Yes, Professor Suresh.
Okay. Thank you for the invitation and the introduction. I'd like to, this afternoon, I'd like to talk a little bit about the plastic problem we have. I don't really want to emphasize on the problem, but I also want to look at what is a good thing about plastics and what is, currently we are talking about the bad aspect of the plastic. So let's start with the plastic a little bit. Before I go into a talk, I'd like to say that this talk is actually designed for beginners rather than the professionals. So a lot of introduction, a lot of general knowledge will be there. But if you have any questions about more depth information you want from our studies, definitely I'll be happy to tell you. And my email ID is given here, and Naveen, the organizers, also have my email ID, so they can you can get it from them as well. Okay, let's continue. Now, let me see if I can. Okay, so the plastic is a general term. It came from the plasticos, the terminology, and then it basically means that it's to shape or to form. This is kind of material where we can mold into all kinds of stuff, right? That's basically how the terminology came. But more scientifically, we call them as a polymers. Polymers are the individual molecules rather than plastic is a common name for a bunch of materials, right? So polymer related to individual structures and their properties. So polymer means, poly means many, meros means parts. Many parts come together and form a long linear structures often. So good, I mean, I have given a kind of cartoon here, a small one sphere attached to form a necklace kind of structures. Good example is an ethylene. Ethylene is a 2-carbon CH2 double bond CH2. Once it polymerized, we can make the polyethylene, which has a large number of such units joined together, and usually with a molecular weight of in millions. Ethylene is a very small molecule, right? If you look at its molecular weight is only 28. So we can generate a million Dalton kind of molecular weight from 28 atomic mass units molecule, right? And that is kind of a power the polymerization has. So polyethylene is just one example. And why these kind of materials are very popular? Because it has invaded all our applications, all our life aspects of day-to-day life. You will see the polymers are inherent part. In fact, we tend to even overlook the presence of polymers in our life. You're starting from your toothpaste has a polymer inside, your coffee mug has a polymer inside, you name it, even food additives, even coffee powder probably has some polymers added to it, etc., etc. So I have given one example here, a bike rider. You will see the starting from wheel is made of rubber. His cap is the helmet is made out of Lexan. It's a polyether ketone, and we have nylon as his backpack. Polyethylene is actually used for his water bottles, and shoes as polyesters and other stuff. So you name it, all kinds of materials are, we have been using polymers and making, molding all these materials very useful for us. Yeah. And that is one of the reasons polymer becomes so prevalent in our life. And these are some common names you always hear in the news or in the scientific literature, where you will see elastomers are basically materials which has elastic properties. Polyisoprenes, neoprenes, and spandex, lycra, silicons, all these has a structurable materials, and it shows significant elastic properties. They are rubbery and elastic. Thermoplastics is an area where usually we call them, I mean, the actual definition is that these are plastic which can be molded and remolded using heat, right? That's why they're called thermoplastics. So polystyrene, polycarbonate, polyethylene, nylon, polyester, there are a whole range of such polymers are classified under thermoplastics. They are usually linear polymers with a long linear chains with a high molecular weight. Their properties are tough materials, flexible, and also it softens with the heat. And these are the polymers mainly we classify as a recyclable material. Yeah. Thermosets is another group of polymer where we the typical example will be epoxides, urethanes, and cured polyesters, and formaldehyde resin, etc. These are network structures which can be molded into certain shapes, and that's it. You cannot remold or you cannot remelt, etc. These are very well, once it forms forever. Right? So these are not able to recycle. Good example is our sponge, is an example of thermosets. They are relatively strong material, inflexible, insoluble, and does not mold in presence of heat either. They just tend to degrade rather than melt. So even though we have lots of polymers available, and then they are produced in a large amount as well. So currently we are talking about 330 million tons per year of this kind of polymers are produced and use it in various applications. This just shows you how many million tons produced per year. And going back to the structure again, you can see a kind of CPK level model. So ball and stick model is given in the short one, which is for a polyethylene, carbon and just hydrogen. And then once you put into the CPK model, you'll see they have a little bit more volume, but they are never a stretched a single linear chains. They're all coiled up shape like structure, and most of the properties are associated with how these chains are organized. Yeah. For example, I give you an example of our noodles. So when you buy the noodles, they are very hard and brittle, right? That is how the polymer chains actually usually arrange, right? They are very randomly organized, but they are still brittle. They interact very strongly, etc. Right? But once you put them into a hot water, in this case, the noodle become very soft. You can pull one chain at a time, but yet they are all coiled up. Right? You can never isolate one of those noodle chains out of this bundle. It always gets entangled and come as a bulk. Now, The same property we will see in case of polymers, where instead of water we use plasticizer for smoothening or softening these polymers. So plasticizers are present in almost every polymer architecture we talk about. Some of the common, very famous plasticizers are phthalate. Phthalate has been used in many polymers, and later on found that they are actually carcinogenic. Therefore, now you can see the bottles comes with a label phthalate free. That means they replace the phthalate with something else, right? And same goes for a bisphenol A is another compound which has been used very heavily by polymer industry, and that also had some biological toxicity. Therefore, they replace the bisphenol A with something else, right? So there is a lot of none of the polymer article which we see around, like plastic bottles or plastic bags or plastic straws, are not pure polymers. They are additives of polymer plus many other small molecules to mold them into shapes and decide properties, decide color, decide architectural advantages, etc. So coming back to plastics, plastics are readily available, very cheap material, very useful material, low-cost manufacturing materials, available with a range of properties. They are mass-produced, 300 million tons a year, and require a less skilled staff in the manufacturing industries. Usually, manufacturing is well settled. There's nothing really goes wrong. The reactors are very huge and works quite very well. They are also corrosion resistant and generally waterproof. Because they are corrosion resistant, they are used heavily in paints. So you will see almost all the metallic objects are actually coated with some kind of plastics to isolate them from the environment. Therefore, we can keep them as corrosion resistant. Lighter than metals, but provide better or similar strength. So some cases where we are slowly replacing the metal application, a good example is the automobiles. Automobiles, many parts are now metal parts are now being replaced by the plastics, because it gives almost equal strength or closer to the metal architectures, and they're also comfortable. They are less lighter in density, therefore the fuel efficiency can be improved. So there are many other advantages of replacing metal with the plastics. But while we use this material, they are never a pure polymer. They are always stabilized with many additives and antioxidants and all kinds of things to improve the lifespan of these polymers in real life. For example, if you buy a plastic chair, we don't want it to be broken down in a month's time or 2 months' time or 1 year time or 2 years' time. We want an extended period of its lifespan. And therefore, the company is known to add many additives to stabilize it and make it stable, right? Stay in the environment for many years. So even after we may finish using it, if we dispose it into the environment or somewhere, it stays there forever, like dinner plates and plastic bags and all these things you see floating around in the environment is because they cannot go anywhere. They don't get degraded. Therefore, it stays there. Currently, due to accumulation of such waste, we have a significant problem in terms of pollution. Many of the landfills are kind of running out of space. Therefore, you see in illegal dumping of waste in many places, and therefore these plastic items being not so heavy material end up in flying in a wind or washed off with the rain water and carry it into the rivers and sea in particular, and they end up accumulating in the ocean or waterways most of the time. Now, if you look around in your house or in your office, in your kitchen, you'll find many such articles. So I've given some example to show that where these polymers are used. So polyethylene, for example, used in making bags and strings and kind of articles, bottles. Polypropylene is another kind of polymer similar to polyethylene, yet used in all these kind of applications. This is polypropylene I just mentioned. So here the only difference is that we have added a CH3 to one of the carbon. So instead of having CH2, you have CH2, CH, and CH3. The CH3 group is an addition or replacing one of the hydrogen. And similar applications, bags and strings and other items are made by these polypropylenes. Then the polyvinyl chloride, PVC, is normally we call them, is another material which is really has a huge impact on the application, especially the tubing industry, where most of the pipes used for water transport, as well as the the putting wires and insulation for wires, etc., are PVC made. The advantage of PVC is that they are non-flammable, unlike polypropylene or polyethylene, because of the halogen presence of halogen. And but yet they provide a very strong mechanical properties and environmental resistance for degradation, etc. So those are kind of advantage. These and the PVC is also called a synthetic leather, and that is also coming into the textile industry quite significantly. Then another common polymer is the PET, polyethylene terephthalate. It's a polyester, and most of our soft drink bottles are actually made out of PET. This is another huge problem we face at the moment, because most of these bottles are one-time use only, and they are pretty good for recycling, but very seldom being recycled because of the lack of knowledge, the sorting out issue, other labels, etc., etc. And then the other common polymer is polyamide. Nylon is aliphatic amide, and used in making these kind of fibers, textiles, other architectures. Yeah, quite a sturdy polymer. Now, to give just a quick summary, US plastic market sizes comes around 1 trillion. And if you look at an application of the various areas where polymers are used, packaging, construction, electrical and electronics, automotive, medical devices, agriculture, furniture, and all those areas, plastic has already penetrated significantly. Yeah. The recent trend is actually the medical field as well, in tissue engineering, as well as biomedical objects are actually made by using these kind of polymers as well, because of the single usage aspects, as well as non-sticking of the biopathogens onto these surfaces, etc. So polymer offers a significant advantages over the other ones, other materials. Now, as I alluded, because of the widespread usage of these materials, often the after usage of this kind of material has no clear approach, because many of the companies who design these materials are designed for application only, and they never design to think of where the material can go after finishing the lifespan of these materials, right? So currently most of them end up in the environment, because the recycling rate is so low at the moment. It's I mean, in most part of the world, it's less than 10%. Only in Scandinavian countries or Europe, it is actually reaching into reasonable levels. Yeah. So one of the challenge we have at the moment we face is that many of this plastic waste end up in the marine environment. So ocean can be considered as a huge dumping ground for this kind of plastic materials. Once it enters the ocean, there is no way to get out of the ocean, because that is where it always end up accumulating, right? Because there is no mechanism to take the plastic out of the ocean as well. Now, not only the plastic enters in the water, but it also cause problem for the living organism as well. So here is an example where the animals are feeding on them. Animals have particularly no taste for these polymers, but most of these polymers are plastic items are contaminated with the food items, and that is where it causes a significant damage. And some of these plastics are recyclable, so there is an economy at the low level where people go and pick up those polymer waste or plastic waste, and then trying to recycle or get some economic benefit out of it. So marine environment is slightly different as compared to land environment, where land, at least there is some kind of shifting or moving of these plastic materials for different application or different terrains happens. In the marine environment, there is very little can happen. It actually go and stay there forever. And only way it can decompose is that by microbial or photochemical. And that is something which currently many groups are investigating, how to degrade these polymers into smaller particles or get assimilated into the environment. It is not as simple as finding a method, but we also need to think about what will happen for these degraded material. Are they safe for the environment, or do they cause even more harm than the plastic itself? So these are kind of consideration at the moment. We are actually baffling or working at the moment, and to make it safer and approach this problem and find a solution. So here is an example of different plastic items, and based on their density, they stay at different depths in the marine environment. So you can see plastic caps being made with polypropylene is very light. It can actually float forever. But same to the plastic bags. For example, polyethylene plastic bags are always on the top. And then polystyrene, the packaging material is also quite light, and it stays again on the surface of the water. But all other ones can either stay in the somewhere in the water, or it can actually sink in at the bottom, right? If it sink all the way to the bottom, it's not a big deal. It is still a big deal in terms of pollution, but it doesn't affect the so much on the biological, the animal population in this marine environment. What is currently happening is that when the animals swim by these waters, they get either attracted to this color and shape of this plastic, and they tend to eat them up, thinking that these are edible materials, and then that end up causing them literally a starvation to death. Right. The other aspect we commonly see is that these material getting entrapped onto their fins or neck, or especially the net fishing nets. Discarded fishing nets are really dangerous to many of these animals, and unfortunately for them, once it gets caught, there is no way to entangle or and no way to loosen that thing anymore. The only solution for them is that eventually either get attacked by the bigger animals, or starve to death in that scenario. So there are so many incidences nowadays. We can see the whales beaching and finding that the stomach full of plastics, shark getting caught on the fishing nets and dies inside the ocean, all kinds of stuff. And there are 5 gyres at the moment have been identified where there are so much plastic accumulated. These gyres are formed because of the water currents, and water currents bring this plastic into different regions of the global ocean. Right. So there are many places, and these 5 places are huge accumulation of these plastics. And this is just gives you some examples of recent whale dead whales with a lot of plastic inside their stomach. Fish get caught, and you can see those plastics inside the fish. Turtles get caught on the fishing nets and other plastic items. So these are some of those things which we commonly see in the news very often nowadays, and I'm sure these things will increase, and there's no way to decrease because the plastics amount are increasing day by day, right? So how to solve this problem? That's the biggest concern at the moment we have. So one of the challenge for the not only this macroplastics or the bigger plastic items are causing trouble, there is also a slow degradation process in which this bigger plastic item actually breaks down into smaller pieces. And by definition, this macroplastics, which is bigger, breaks down into a piece which is 5 millimeter or below. We call them, those pieces are microplastics. Yeah. This microplastic can further undergo degradation, form a nano-sized particles, which is called the nanoplastics. Now, microplastics are also being prepared by certain industries and added into products especially in the cosmetic industry, and that now getting banned by many other countries. And that also ends up in the ocean. And these are smaller because the size is so small. They are attractive material for many marine animals to feed on, and that is causing a significant damage to the ecosystem of marine environment. So that is where we are actually currently spending a lot of time to understand what is the environmental impact of these materials onto the marine animals as well as the terrestrial living organisms. So this microplastic can come in two ways. One, either via degradation of the existing plastic waste, or through the products in which the microplastics were added for different purposes, right? So both are getting accumulated again in water. And I've given some definition here. Macroplastics are much bigger in centimeters or meters. Microplastics are somewhere between 1 micron size to 5 millimeter, and nanoplastic is usually submicron, right? Hundreds of nanometers or tens of nanometers. Multiple sources it ends up, yeah, from washing machines and for cosmetics and name it. There are lots of such material ending. There has been some studies on environmental surveys, and this is done in Europe, the Rhine River, and they were actually identified in the Rhine River. There are lots of microplastics present in the sediments, and some of them have been identified by the which polymer it's contributed to, etc. Microplastic is also extracted from various facial scrubs and other products, and then some of the animals have been, the histological samples of animals' liver and other wild animals is examined, and then some of these particles has been identified in those tissues as well. So to come up with this program, we have different stages. We can identify now the plastic in the environment. We have done a lot of surveys around Singapore and the regional countries. We are going to do even more in the coming years. So there is no question about how much is present. There is a huge amount present. But what is not really clear is that what is the impact of these plastics on to the environment. So there are some already have some evidence, like for example, lack of degradation pathways. We know that these plastics are not degrading very fast enough. So there is a quite significant accumulation on these bigger plastic items and slowly releasing small particles. Because of that, they are going to stay in the environment for a long number of years. Cause significant damage because either it actually being eaten by the marine animals and they die, or it actually accumulates and cause damage to the other ecosystem altogether. On top of the plastic itself, there are a lot of additives inside, and they also leach out from this plastic and cause damages and reduce oxygen content in the environment, etc., etc. So there is a huge number of problems which we face in this kind of scenarios. The bigger question we would like to address is that what does it do for the human health? Because we know that it is actually present in the environment. We know that marine animals are eating them up, and we also know that there are a lot of us are fish eaters, right? We get the fish directly from these sources where which is contaminated with so much plastics. So at the moment, very little information is available what it does to the human health. There is a concern continuously arising because the concentration of these kind of plastics are increasing every day, right, in the environment. So it is going to cause more and more trouble in the future years to come. Do enter human cells. Our own experiments and other groups and experiments have shown that these tiny particles can actually easily penetrate through your from food to your tissues, your cells, etc., and get transported to different parts of the body. And once it's there in the cell, it actually induces stress to the cells and create all kinds of reactive oxygen species and other interfere with the cellular mechanism. And because of all these things, what is the long-term consequence for human health, and or what is the long-term toxicity of these materials? So that is currently where we are trying to answer some of those questions, and we have our own methods and models we pursue to come up with answers for such problems. And then there are a few other groups working on possible alternatives to the synthetic polymers. And this is a very horrendous task because the amount of plastics which we use is significantly high. And there is currently there is no real replacement or substituents for these kind of existing plastics. So one thing we highly desired in the new plastic should be after our usage the plastic should degrade, or after our usage the plastic should be coming into the in a circle where it can be reused and as efficiently as the virgin plastics and stuff like that. So these are kind of very conflicting demands. For example, if you think of making a plastic material which can degrade after your usage, who decide how long we want to use this plastic? And if we say it's 2 months, it will be a very short period of application for certain very short period for certain applications, but very long period for another one. So the time is a critical factor. Second, if you want to design polymers which can come into recycle, often these kind of polymers are not always used as a pure material. It is actually additives of many compounds. So how do we selectively remove this material from the after usage of plastics? So there are lots of such technical questions at the moment. There is no answer for it. So, but there are research being done to change it, right? So current challenges are how do we remove and valorize the existing and future plastic waste. So when we talk about circular economy of plastics, we need to see what can we do with existing plastic waste and how to bring them into the value-added products. And then if you are going to come up with a new plastic, how does it fit into that circle? And how to understand the human and plastic interface. When does it have to be stopped? Our demand versus the toxicity of these materials. Develop new substitute for plastic with similar or better properties, and develop new standard testing methods. Those are not existing and doesn't exist at the moment, so we need to come up with the new things. So what I'm going to talk about the remaining time is to show you some examples of what we do in our lab to look at how these plastic particles are affecting the human health as well as the marine health, right? Effective living system, there are a bunch of toxic aspect we can think of. One is the polymer itself. The other one is the the compounds coming along with the polymer. That's two things we need to keep in mind. And some of them are damage to organs and tissues. There are lots of toxicity information available, etc. In some cases, if they are pure polymers, some polymers are not toxic even. So we have to consider all these aspects. I already mentioned that there are many fish which eat these plastics, and therefore people have been detecting this kind of particles all over the place in the fish. And also there's a whole plastic chain exists in the marine environment now, where small plastic particles with the size of algae, which is actually or plankton, which is the feedstock for many of these animals, they tend to get mixed up, and so the bigger animals tend to eat them up, and then the bigger one start eating up. So these plastics now become the first step of the food chain inside the marine organism. That causes a significant problem too. Now, when we talk about the plastics, there are two aspects we look at. One is the polymer by itself. The group of polymers we call plastics. So the polymer, I already given you structures of polystyrene, polymethyl methacrylate, polyvinyl chloride, etc. I have given here. But when you look at the smaller molecules, or where it started from, like styrene and methyl methacrylate and vinyl chloride, they're all very toxic. The toxicology of those small molecules are very well known, but yet the toxicology of the polymers are simply not known at all. That is, I mean, I can only speculate that the reason why people have not emphasized the toxicity of polymers is that often this is considered as a huge molecule, and therefore entering into cells is kind of difficult, or getting into aqueous medium is difficult because they are hydrophobic. So in the old days, those are kind of constraints we had. But when the plastic ages, some of these properties do change. The molecule tend to degrade into smaller fragments, and also the air oxidation or photochemical oxidation changes the hydrophobicity to make them partially hydrophilic, so then they can actually enter the cell as well. So there are lots of changes happening while these kind of plastic materials are in use, or after usage, when we dispose into environment. This kind of chemical transformation also happens, and that actually contribute to the entry of this plastic into the marine, into the living system. Okay, as I mentioned earlier, there is a whole range of things we need to consider when we start working on it, as surface area of these particles, and what are the other chemicals involved inside. How does the chemicals put into plastic actually enter or come out of these plastics when it consumed, and then are they accumulative poison, or are they get degraded and disposed of, etc. So a few parameters we currently work through it, and when we think about our current systems, for the time being, we do not know exactly what's the concentration of these particles in the environment, because it keeps on changing, first place. Second, due to the water movement, it's not constant. It actually varies from place to place. Third, the shipping industry is so prominent, and they contribute a significant amount of this kind of waste into the environment. Very little laws and regulations manage these kind of activities. Yeah, so we want to find out understanding health and impact of living organism in presence of these microplastics, and possibly come up with the solutions. Right? In our lab, we work on PMMA and PVC, PVAC, polyvinyl, pyrrolidine, so those kind of polymers, and we make our own particles. The biggest challenge for this kind of research is that since these polymers have no optical cross-section, so they don't absorb in a visible range or a UV range. Therefore, tracking them in a biological system is extremely difficult. So what we have been doing is that we have been tagging these polymers with a fluorescent dye, and therefore we can actually monitor the path were followed by these particles. And we make a nanoparticle in our lab using these polymers and the fluorescent dye, and that nanoparticles are relatively easy to enter into a living system. So for our models, we use a synthetically nanoparticle made in our lab with the fluorescent tag. The mechanism is, the methodology is well understood. You can either start with the monomer of the polymer or the polymer itself, and then we do a kind of precipitation method to get the particles. And these particles at the they get dispersed in the water quite nicely because of the small size. Plus, we also add a small amount of the surfactants to stabilize these particles inside the aqueous environment. So if you look at the solution, they are pretty clear. Right. So the middle one is the polystyrene latex, which is commercially available, but the other ones are actually we made by ourselves. Clean water is on the right side and the nanoplastic is on the left side. So you can see the water and the nanoplastics are almost transparent. Okay. So I mean, this is just a way to make these things just a quick and fast precipitation method. I mean, in my lab, even high school student does this precipitation, so you don't need a very sophisticated method. We know how to do this, and we have a protocol for that. And once you make it, you can get pretty much a mono dispersed size anywhere from 100 to 300 nanometers. And usually we work around 130, 150 nanometer range for the polymers I mentioned earlier. And this is some of the zeta potential and the size given in this table. You can see most of them are negatively charged. We are making the positively charged particle at the moment. So far, we have been focusing on the negatively charged particles because the surfactant is quite not toxic to the living systems we use in making the negatively charged particles. The size, as I mentioned earlier, it's around 200, or we actually start from 130 to 200, 250 range size. And because we put in optical dye, we can actually now monitor these particles using either absorption spectroscopy or emission spectroscopy. And this is quite nice for us because even tissues we can image by using these particles. I'll show you some examples in the next slides. So in my lab, we use two models. One is a cellular model where we use the commercially available human cells, and the other one is the animal model where we actually use live animals, especially marine animals. So I give you two examples of, or one example each for those things. So cellular models, we do a lot of biochemical assays using human cells. Alamar Blue assay, reactive oxygen species, ATP concentration. We do quite range apoptosis assays and other assays. So here, what I'm showing is that the first image here. So the bar graph shows that concentration dependent viability, and that means how many cells are viable at different concentrations. So here we go from 0, which is the control cell with no particle added, and then the maximum concentration we use 200 microgram per ml. The black one is PMMA, and then the red one is PMMA plus the dye incorporated. So we have both particles, one pure polymer, the other one is polymer plus the optical dye. And as you can see across the both behave similarly, right? Because it's a polymer which decides the toxicity rather than the dye. Dye is just to see the particle. And here we have shown that the green emitting dye we can see inside the cells. The nucleus is stained blue, but the polymer particle actually shows up as a green emitting particle. So you can see around the nucleus you have lots of particle accumulated inside the cell. So this particle has no problem entering the cell, but once it enters, it simply stays there at the moment because there is no mechanism for the cells to degrade these particles inside the cell. Yeah, and we can actually track them, how fast it gets into certain cells and where does it go, etc., etc. So we do a lot of such tracking using these fluorescent polymer particles at the moment. In the case of animals, we do use a bunch of marine larvae because the larvae are usually transparent, so it's easy to image. So in that case, what we really wanted to do is to look at the toxicity of these nanoparticles in these larvae, and then interaction of these nanoplastic with their feed materials like microalgae and things like that, uptake and distributional studies, and then retention of plastic. So how long particle stays inside the system. And then we also monitor the physiological changes at different stage of this larvae. Do they influence the developmental cycles of these animals? So one easy example is the barnacles. Barnacles is like a shellfish which grows on everywhere. I mean, this is a nightmare of the shipping industry because all these barnacles get stuck onto the bottom of the ship, causes the friction, creates a huge energy bill for these ships. So they try to prevent them sticking. But our interest is to see how the life cycle goes on, right? The barnacle actually releases the napoli, which is the larvae for them. And then napoli actually takes 4 days to get into a civet kind of range where it tend to settle onto a surface. And then from there it become a juvenile, and juvenile become adult. So within a week or so, you will see this cycle actually gets completed. Yeah, so that's one of the reasons the spreading of barnacles is very fast. And it is good for us because in this case, we get at least 4 days to study the transparent larvae of these barnacles. And based on that, we do a lot of control experiment as well. It's not just, so we make sure that our particles are stable, they don't aggregate, they stays in the system, they don't degrade, they don't release the dye. There are lots of such questions we address along the way. Yeah. With the feed, we don't see any kind of interaction at all. The algae doesn't even take it up because that's quite understandable because algae doesn't feed. Algae is a kind of plant material where it has its own chloroplast, which relies on photosynthesis to make the food. So it has absolutely no toxicity, irrespective of what concentration we use. But for the barnacles, we can see them consuming these particles, and then if you monitor the digestive tract, we can see the particles are along the digestive tracts as well as all over the place. So here is an example. I don't know whether I can see the here. What we do is that we take one of those barnacles and we can do a 3D imaging to show that the barnacles, the whole body is full of these kind of plastics. And that is what we have shown here by doing the 3D imaging. Let me go to the next one. So for the barnacles, we can actually do at least two type of exposure studies. One is acute exposure, the other one is chronic exposure. So usually the acute exposure means you are the animal is exposed to a large concentration in a short period of time. Chronic exposure means the animal is put into a place where the concentration is very low, but it is exposed to a longer period of time. That is actually what happens in the environment most of the time. Very seldom we have this huge release of pollutants and then kill everything, right? But in the real environment, we have a low concentration, but exposed a large amount. So here we have a control in the left column. Middle column is the acute, and then the right column is the chronic. So you can see in the acute, where large in the control, we don't have much of a fluorescence from the green particle because they are not exposed to it. There's a little bit of background signal because the natural material also have this green fluorescence. But if you look at the acute one, where the barnacle is exposed to this high concentration, you will see most of the places you will see some green fluorescence coming from the body, right? But when you look at the chronic one, you will see there is a significant uptake of these particles and significant accumulation of this particle inside the body of the barnacles. And they tend to eject a little bit, but it's not as high as whatever it takes in. So a lot of things get stored inside the system as well. And we can actually image them under different conditions. The green fluorescence primarily comes from the particles where what it's has eaten. So here you can see different stages of the napuli or barnacle larvae. The top one has top and bottom has both everywhere the particle. It's not just the digestive canal, right? So here is another images of the different stages between the napuli and the cyprid state. Again, you can see they are having these particles everywhere, right? Some of these things, napuli, when they grow, they tend to molt out. Or even the molt has the this particle. So you can actually, this is one of the molt collected from one of the animals. So this green fluorescence comes from our polymer particles. Now, this is not just the barnacle napuli. We also has done some fish and shrimp samples. So here is an example of a shrimp larvae, which just hatched like a day before, and then given the feed of this polymer particle, and you can see the entire digestive canal is full of these polymer particles. Yeah? And they tend to ingest out as well. They tend to poop out. In the bottom figure, you can see some of those things coming out of because none of these animals have any digestive enzyme for removing these particles. So they have to be just get thrown out. Unlike a barnacle, in this case, the spreading of this polymer particle is very minimal. We haven't seen so much of a spreading. So it is kind of species dependent. Not every animal takes up and distribute the polymer particle along the way. So in conclusion, I have actually shown you some of the advantages of the polymer, in which we are so closely related to the polymers, and there is no way we can say tomorrow onwards we will ban all the polymeric articles. Then the life become very miserable all over the world, right? So no government can take that kind of drastic actions. On the other hand, the wide usage of such a polymer increase the pollution in the environment, and that is going to go on forever. That's the sad part of this kind of convenience provided by the polymers. Right. So what we really need to have is that much more research into both sides, where we need to design new plastics with the whole lifespan of the plastic in mind, and the other side we need to understand what can we do with the plastic waste and how do we make use of it, and what kind of health aspect we are actually talking about. So both areas are currently being investigated by different research groups, and we do a little bit on the environmental impact of these polymer particles. So how can everybody help? All of us can help to some extent. We can actually do a reduce, reuse, and recycle kind of thing. We can intentionally reduce the plastic usage. Many of the articles which you buy, don't dispose it immediately. You can reuse it, and then also trying to recycle it. And while recycling, you look at the plastic, all plastic items have this triangle at the bottom or on the side. And the smaller the number, the better the recyclability of these materials. So if they're 1 or 2 or 3, they are all easily recyclable. So every one of us can actually participate in the reducing the polymers ending up in the environment. This is just a comparison. In the old days, there used to be a argument that paper bags are much better than the plastic, but in reality, the paper bag is equally pollutant than the plastic. Even though paper degrades in the environment, to produce the paper, we need to spend a lot more energy, as well as the lot more toxic chemicals like bleaching agents and things like that. So paper is not really an alternative solution for the reducing plastics. We need much more intelligent materials for that. So I think that is all I have to talk today. And I hope that we'll have much more interesting information in the future. So let me thank all of you for your time and your interest, and thank you. If you have any question, I'll be happy to answer as well. And thank the organizer for giving me this opportunity to talk about it.
Thank you very much, Professor Suresh.
I Hi, thank
for
you.
this talk on the topic of immediate concern and sharing with us the information about the methods you are trying to use to tackle the plastic problem.
Yes.
We are actually running out of time. I see we're running 20 minutes late, but I think we can take one short question.
Okay. Sure.
So anybody has questions, please, you can raise the hand. Or we can go to the next speaker. So if you want to ask something, as Professor Suresh told you, you can actually email him. Okay, I see a raise on hand. Dr. Shiva Subramanian.
Okay,
Sir, I just joined in the later part of your talk, but I would be very happy if you can share some light on the influence of our water bottles, because I
Yes.
have just read about something about the same water bottles that, especially in Kerala, we use more of those cumin water and those kind of things which we
Yes.
normally the students take. So this kind of phenomena can also happen in that.
Yes.
Just some light on it, sir. Thank you.
Right.
Thank you.
So the common rule of thumb is that you try to avoid as much as possible the use of plastics, right? So if you put a hot cumin water into a plastic bottle, it will tend to leach out plastic, small molecules from the plastic to the water, right? Higher the temperature, the higher the leaching rate, right? Some of these cumin compounds also has the higher leaching ability, or not only cumin or other, the plant-based materials as well. So common rule of thumb is reduce the amount of plastic you use. Use a glass bottle or even a steel bottle, those kind of things, metallic copper bottles, and those kind of things can also be improved. Now, I think in India, there is a bamboo bottle being circulated or made by different NGOs and companies, etc. And those are kind of things would be more healthier options as compared to plastic.
Thank you, sir. Thank you. Very kind of you.
Sure,
Thank
sure.
you.
Okay, thank you.
Thank you, Professor Suresh, for your time. And
Thank
then
you.
maybe in future, we'd like to have you here in person and
Sure, sure.
talking to our students.
Yeah,
Thank
no
you. Thank you
problem.
much.
Okay, bye-bye.
Now we'll move on to our next speaker. We have Professor Halgeri from PPISR Bangalore. I request Mrs. Divya to give the brief introduction about Professor Halgeri.
Naveen sir, am I audible?
Yes, ma'am.
Good morning, one and all. It's my honor to introduce Professor Anand B. Halgeri to the audience. Dr. Anand B. Halgeri is currently working as Director of Purna Prajna Institute of Scientific Research and coordinating the entire research activity in catalysis, material science, and biological sciences. Dr. Halgeri has received his PhD degree in chemistry from Bangalore University and carried out postdoctoral work under UNESCO Fellowship on Industrial Catalysis at Chemical Engineering Department of Tokyo Institute of Technology. He joined Indian Petrochemicals Corporations Limited, Baroda in 1976 and has provided sustained leadership as Senior Vice President and Head of R&D there, and later served the Reliance Industries Limited. He has numerous research papers in peer-reviewed national and international journals and has obtained 36 Indian and international patents. He has been a life member of many scientific and professional bodies both in India and abroad. In recognition of his outstanding contributions in the area of heterogeneous catalysis for 3 decades, he has received several national awards and honors, which include the ICI India Limited Award of Indian Institute of Chemical Engineers, Lifetime Achievement Award as Eminent Scientist in Catalysis by the Catalysis Society of IIT Madras, the Vasvik Industrial National Award in Chemical Science and Technology, Professor K.G. Naik Memorial Gold Award of MS University, Baroda, and many more. He has been advisory member of several professional bodies, various academic institutes, Department of Science and Technology, CSIR, IOCL, and Reliance Industry. Today, we are highly fortunate to have Dr. A.B. Halgeri here for ICMSE 2020. The title of his today's presentation is Development of Novel Mesoporous Catalysts for Conversion of Biomass into Fuels and Chemicals. On behalf of Organizing Committee of ICMSE and Amrita Vishwavidyapeetham, I invite Dr. Halgeri to deliver his talk. Thank you.
Professor Halgeri? Professor Halgeri? I think your microphone is muted.
Is it okay?
Yes, sir. Yeah, now we can hear you.
Is it okay? Are you listening?
Yes, yes.
Okay.
So
can you
I
make
have shared, yes, I have shared the PPT. I think you all can see it.
I can see it. I can see it.
Okay. Okay, sir. Yeah, we're good to go.
Okay. Thank you, Dr. Naveen and the organizing committee for inviting me to give a talk on the International Conference on Advances in Material Science. Okay. Okay. Is it visible, Naveen? Okay.
Yes, sir. Yes.
Okay. Thank you very much. The topic of my today's lecture is on development of novel mesoporous catalyst for biomass conversion to clean energy and chemicals there. Basically, I come from industry, basically from Reliance industry, where we are working mostly on the energy related catalytic material and its application. Some of these areas we have continued research after long years of industrial experience there. Can you give the next one? Next slide, please.
Yes, sir. You see it.
Okay. Okay.
So I think there is some time lag. So
okay. Okay. I will we'll go by your advice. Okay. I think the basic idea is of outlining the presentation is introduction. Introduction is basically, as we all know, that we get most of the oil and chemicals from fossil industry, and India is importing around 85% of oil from Middle East, and then we process it through refinery, and then we make petrochemicals, chemicals, and varieties of energy materials from the oil which we import from abroad actually. And the idea is, can you switch over to alternative source of energy that is basically renewable energy sources like biomass conversion to chemicals and fuels. So that will be the alternative approach of looking materials away from the synthetic fuels or from fossil fuels which you are importing from abroad, and also to reduce the import material as much as we can use renewable materials. I think that will be the future. We must try to utilize as much as possible renewable sources which are available, or we call it sustainable energy for future requirement. So in this, this is the basic introduction of my talk, and I'm going to cover some of these chemicals that we have produced from biomass to chemicals and fuels there. In that way, we have used several catalytic processes, that is preparation and synthesis of catalytic materials, and those novel materials we have one for full type characterization, then we look for application, and then finally the conclusions. Next slide, please. Okay. So this will be a kind of preliminary information to some of the doctor student and master course student. We are trying to utilize porous materials. They are of interest because there are many advantages such as large surface area, enhanced accessibility, and ability to anchor different chemical functionality on the surfaces. So in the materials, we have got several type of materials. Porous materials have of current interest, as I mentioned, because of large surface area, large number of active sites present on the surface. This slide shows the individual. Okay. Most generalized definition of porous materials is continuous networking filled with voids, and it can be filled with gases. These are the small pores which can be filled up with gases, and basically individual small alkyl chains length quaternary directing agents are used for synthesis of this material, and they form the porous material there in the system there. They are mostly alkyl chain or surfactants are used during synthesis, and they use aluminosilicate, sodium hydroxide, and organic templating agent to synthesize the porous material. The next slide shows the details of preparation. Next slide, please. The history of porous metals began with the zeolites having aluminosilicates, because historically zeolites are known more than 50 years now. The first patent came in early 60s, which is used, so they're all mostly sodium aluminosilicates. We used to call 5 Armstrong, 6 Armstrong, and these are the molecules used for gas separation. And then the biggest discovery came of zeolite is ZSM5 type zeolites, which have been extensively used in all refining and petrochemical industries. And taking that clue of aluminosilicates or zeolitic material, then we started with new porous material of different pore structure there. So if you go for the porous classification, porous materials can be classified according to the pore diameter. One is micropore, pore size less than 2 nanometers, mesoporous to more than 50, less than 50, and macroporous is more than 50 nanometers. So these are the pore size determined 2 nanometers, 50, and bigger, larger is around 50 nanometers. The whole idea is to synthesize large pore molecules. Generally, zeolites are around 5 to 6 Armstrong, but we would like to go for a larger porous material, more than larger diameter, so that large molecules can enter into the zeolitic pores and carry out the reactions there. Next slide, please. Basically, these porous materials have, depending on the building framework. Building framework can be purely inorganic silica, alumina, or metal oxides. Basically, we can make nanoporous silica, nanoporous alumina, and even metal oxides can be made nanoporous with large diameter. This is the class of compounds are coming to existence there. This is the first class of materials, and still the work is going on. The second class of materials came organic, inorganic hybrid materials there. They are also being called MOFs, have become very, very important material there. And third is inorganic piezoporous materials through soft templating agent route, then they can be synthesized in the system there. These are some examples. They use micellar reagents there, soft templating agents there, and we can make composite inorganic mesostructure, solid surface structure, and the kind of materials they use, the mesoporous material is shown as MCM41 with large pore material have been synthesized through the soft templating agents, which have been currently using for certain application. MCM has become now widely used in even many chemical industries for fine and specialty chemical synthesis. Next slide, please. These are some of the hard templating agents they use. The surfactants are put into the system, and then we have to remove by heating, and then we add some precursors, and the carbon which is deposited during templating agent, they have to be removed through by heating around 500 centigrade. Then you can get silica supported porous structure material there. These are used for the hard templating synthesis there. Next one. Now I will give you a little briefing on synthesis route for mesoporous material. basically templating structure. One is soft templates and hard template. In the template structure directing agents, we use organic templates, and then mesoporous silica and mesoporous carbon materials are synthesized through hard templating agents. Then the next second is mesophase control. Tunable architectures and surface properties depend on pH value and surfactants, temperature, etc. These are soft endo template. Then in the hard template, we use the fixed and restricted by the pre-formed structures of hard template. Then pore size you can get uniform and narrowly distributed. And in the hard template, we get relatively wider than the hard template. So these are the next is prospect, low cost, convenient, suitable in large scale manufacture. I think this is the soft templating synthesized materials are low cost, convenient, and suitable for large scale industrial application. That is why you can see MCM 41, SBA 15, tin oxides can be prepared in large quantities and find a lot of catalytic application there. Compared to the hard template, it is only MK1 has been example, and right now most of the mesoporous materials are synthesized by the soft templating agent, which is currently can be applied to many large scale industrial application. Next one. Generally, I have shown you the synthesis. There are two types of work I'm going to present in this talk. One is mesoporous inorganic materials like mesoporous tin oxide, and the other program is the emerging materials is mesoporous polymers. They are not very well known as of now, except last 10 years, some work is coming on mesoporous polymers, whereas mesoporous inorganic materials have been very extensive done. I'll give both the examples of this macroporous material, both inorganic as well as polymer. This slide shows basically how to synthesize the mesoporous polymer, divinyl benzene and azobenzene nitrile and tetrahydrofuran and water. You can synthesize under hydrothermal treatment and you get polymeric material, and these are all under conditions 60 to 100 degrees centigrade temperature synthesis, and you get mesoporous polymer. These are all a new class of mesoporous polymeric material, and we would like to use this material for varieties of applications. Next slide, please. The other approach we have done here is mesoporous porosity from microporous to aluminosilicate material by desiliconation. Zeolites are very well known, as they are all aluminosilicates with no structure. But we would like to remove some of this aluminum from the resources, so we can go for etching using sodium hydroxide etching. Then you find ZSM5, this term desiliconation. There you would try to remove a silicon from the zeolitic surface is called desalination, and we can create mesoporous through this way also. We can create mesoporous from zeolites using etching technique like sodium hydroxide. These material also known called high activity zeolite material or nano zeolite structure material, which are of current use. Microporosity can be irregular sometimes, but nowadays they are finding some application on the etching kind of zeolite taken from sodium hydroxide. Next one. Now, the first part I covered up was varieties of zeolites, and then they are all basic raw material support materials there, but they cannot be used them directly as a catalytic material there. We need to be done functionalization of materials. That means we have to modify the materials there. Modification of materials can be done by post modification, XU2 generation of acidic sites by grafting. That is called sulfonic acid group. Then aluminum you can incorporate to make it more acidic. The second part is in situ generation of active sites. Third part is incorporation of active metals ion on support. Some of the active metals like nickel, platinum, palladium, which have high support material for hydrogenation, dehydration reaction. So we have to support on mesoporous material active sites functionalization on the surface there. Then the last one is ion exchange of active metals. There is zeolitic material, we can put ion exchange, and then metal incorporated material, mesoporous materials also become very, very active. So functionalization of materials becomes very important to make them active materials using nanoporous materials. Next one slide, please. Okay. This is one way of making grafting sulfonic acid group. Here we are trying to do is we have used mesoporous polymer, which we have synthesized in the earlier slide. Mesoporous polymer has no much functional activity. If you want to make acidic function of this group, grafting, that is post-synthesis functionalization of organic modification, mesoporous silica phases, or with terminal organosiliciate type. So we can graft it through sulfonic acid, either in basically in mesoporous inorganic materials or mesoporous polymeric material. Grafting is very important, create some acid function for acid catalysis reactions. Next one. This is another example for grafting of sulfonic acid group. The left side shows all mesoporous polymer materials. The right hand side shows the materials like MCM type large pore mesoporous material, where you have incorporated sulfonic acid group by impregnation, then activating, making more sulfonic acid. The sulfonic acid can be sulfuric acid of different concentration, and you can increase the acidity by adding more number of percentage of sulfonic acid to create more acid sites on the catalyst surface, both at the mesoporous material as well as kind of an inorganic mesoporous material. Next slide, please. These modified zeolites can be used for various applications. The next is synthesis, direct synthesis through co-condensation. This is a tetraethyl orthosilicate, and then organically have been used silicates, and then synthesized under autoclave temperature. And these are diagrammatic representation by direct synthesis for the organic modification, mesoporous, either silica or organic functional groups can be utilized for synthesizing by co-condensation of mesoporous silica, mesoporous tin oxide materials. Next one. This is the in situ oxidation synthesis strategies for the preparation of sulfonic acid modified mesostructured materials there. And this is the block copolymer, and then complete dissolution at 40 degrees centigrade, and then MTPS, then hydrogen peroxide aging, then ethanol washing. And finally, we can use micellar emulsions or tetraethyl hydrolysis, silane incorporation, or in situ oxidation, aging and surfactant removal. These are propyl sulfonic acid, antimony, SBA15 type of zeolites. It's kind of one example how surface modification can be made through sulfonic acid mesostructured materials. Next one. After this is another example where you have to creation of active metal sites on catalyst support. One is the catalyst support. It can be mesoporous inorganic material or zeolitic material. Then use metal precursor. It can be tin, nickel, platinum, palladium, chloride or nitrides have been impregnated this thing, and then impregnation material on the surfaces. It can be done generally 0.5 to 1%, 5%. Small amount of dosing metal will be incorporated. After impregnation, you go for drying, and then you can get metal supported catalyst system. So this is creation of active metal sites on the catalyst support. Next slide, please. This is another example like on sulfonic acid functionalized mesoporous polymers. This is divinyl benzene and azonitrile, butyl nitrile, tetrahydrofuran and water. And then you go for hydrothermal synthesis, then you make polymer, then you go for sulfonation, and then you make sulfonic acid mesoporous material, which has lot of acidity on the surface catalyst system. These are all sulfonic acid functionalized mesoporous polymers. Next slide, please. And these are all acidic in nature. Next part, I spoke about the introduction. I gave some examples how to synthesize mesoporous material, both inorganic and organic polymers. And then we have used to characterize these materials through varieties of sophisticated techniques. The next one, please. As usual, generally people go for X-ray diffraction to the structure of materials. Then next important is nitrogen absorption technique, pore size and surface area measurement. This also gives you surface area as well as pore size distribution to find out the active sites on the surfaces. Then comes the temperature program techniques to measure the acidity and basicity of these materials. Once you make acid functions on the support material, would like to find out what is the acidity and acid strength distribution on the surface of this catalytic material. And similarly, if they are in basic in nature, the catalysts are base catalyzed, then you can determine the basic properties on the catalyst surface through temperature program desorption techniques. So it is ideal to find out the number of active sites on acid sites, number of basic sites on the surface properties, so that can be correlated with various catalytic activity. Then comes chemical titration. Some of these organic polymeric support material like mesoporous polymers, they look like ion exchange reagents. Their thermal stability is very, very low. So in order to measure the acidity and basicity of these mesoporous polymers, you use some chemical titration method to determine the number of active sites on the catalyst surface. Then comes atomic absorption spectroscopy for metal estimation. At small percentage level, you can determine. Then scanning electron microscope, and you can also use TEM for the ordinariness of the materials. These are general techniques that we have used in characterizing the various set of catalysts that we have prepared. XRD, I don't want to go in details. These are all well-known techniques, and we have done intensity, 2 theta values intensity, propyl sulfonic acid organic, and these are the nitrogen absorption studies to determine the pore size, and similarly pore size distribution also have been characterized. Propyl sulfonic acid and propyl organosilicate compounds, pore size, pore volume, to account the number of active sites present on the surface there. The next important technique is to find out a number of acid sites or number of basicity on called temperature program desorption technique. This is temperature decide amount of active sites, that acidity, basicity, then hydrogen intake, and so on. These are the most of the things. If you want to determine the acidity of catalyst, ammonia is get absorbed on the acid sites, and then we allow it to go for TPD, temperature programmed desorption. The x-axis and y-axis we have put up, use the TCD signals, and then temperature desorption from 100, 300, 400, 500 centigrade. The curve show the lowest temperature around 200 shows the weak number of acid sites, which can dissolve very quickly. The second one shows medium sites around 300, 350. They call medium sites, and the last one is generally 500 to 600 shows the long, strong acid sites. So these are all, we can determine acid strength distribution for all catalysis there. Similarly, we can do basicity using carbon dioxide. Sometimes we have to use hydrogen. Hydrogen used for chemisorption of active metal surface on the catalyst surface. These are all techniques used for characterizing the acid and base properties of the on the catalyst surfaces there. Then we can use chemical titration used for materials with lower thermal stability, like ion exchange resist or mesoporous material. Their stability is around 250 degrees centigrade, and they cannot be too strong. So in order to use the acid and base properties, we use chemical titration methods, and AAS is for some metal incorporation that has been done in some cases. Next slide, please. So the most important topic I have coming here is the biomass into fuel and chemicals there. I have mentioned that due to the medium-term depletion of fossil fuels reserves and growing scarcity of fossils, hydrocarbon, researchers around the world are motivated to search for an alternative source of energy. I think this is more applicable to India around the world, especially some of the countries like Brazil and European countries are completely trying to avoid importing fossil fuels from Middle East there. They are almost using all the fossil fuels from the through the sustainable route which are available in forest, cellulosic material, or through biodiesel, bioethanol, this kind of an activity there. So biomass is an alternative source of. This is the idea is to avoid importing as much as fuel oil from abroad, and to make indigenously how we can make through biomass, so that we can avoid large import of fossil fuels from Middle East there. So the economy of this country can be improved if we can start using biomass which is available in this country. Second important is the biomass is the fourth largest energy source in the world for the generation of heat and power. The first one is oil. Oil we know everyone. Then comes coal. Then comes natural gas. Nowadays people are going for solar and then wind energy and all those things. But currently biomass is the largest energy source which is available in forests, wood materials. Even wherever you grew a lot of crops like wheat and rice fields, the lot of cellulosic material is still available for utilizing it there. So idea is it has been recognized that all the renewable carbon sources to produce varieties of value-added chemicals, functional materials, and fuel products due to abundant availability in nature. I think we are trying to focus is the last part, how we can use renewable carbon source to value-added chemicals and functional materials and fuels, and which is abundantly available in nature. This is called sustainable chemistry or renewable source of energy, and trying to avoid as much as possible imported oil, which this country entirely depending on us. So that was the whole focus of our research in application of this mesoporous material for application to alternative source of energy. Next slide, please. So this is the biomass. The left side shows hydrothermal stable catalyst, and then we can make fuels and chemicals through the conventional route. Another is to make biomass there. Here I am giving you the example. The left side shows you ethanol. That is called this thing. Then comes starch. Then these are all lignocellulose material, and then you can platform chemicals you can make, and then you can. These are all used for various purpose there, and these are all cellulosic material coming from natural sources. I say cellulosic material, and then platform chemicals can be made. The other one is diesel fuels, and these are all non-edible abundant, which is available. Also can be made biofuels on the system. The right hand side shows again cellulosic material, sugar cane. All these materials can be converted through hydrolysis to make some valuable biomass material for starting, which are available abundantly in the country today. Next slide, please. Yeah. This is the left side shows currently how you are making petroleum and gasoline is from petroleum refining industry, petrochemical this thing, and then we can make gasoline, jet fuels, and diesel. This is conventionally used now. We are all making like that, but you generate a lot of CO2, and that is left to atmosphere. Then the right hand side I'm showing biorefinery. Biorefinery means through bio route. Biorefinery is made biomass renewables, and then ethanol, biodiesel, gasoline, jet fuels can all be made through biomass. CO2 is produced, and then through atmosphere and through photosynthesis again, it goes back to biomass. So it is a renewable source. So this biorefinery has become more important currently, so that we can use through biomass, and then we make all chemicals like ethanol, biodiesel, gasoline, jet fuels, and then recycle to CO2, then photosynthesis back to the system there. This is, you can make fuels, and once you make fuels through system, you can get ethanol. From ethanol, once you get from, these are the left side is biomass. From biomass hydrolysis, you get hydrogen, you get through steam reforming, and then you get ethanol, and then gas blending, you can do it. Once you get ethanol, you can make ethylene, you can make propylene, you can make butadiene, which can go into the petrochemicals. So ethanol, which is produced from biomass, can go these chemicals, and some of them can be utilized for making fuels out of the system. And you can see the application of varieties of gasoline and plain and ATF and all those things. This is the end application of the biomass to varieties of energy materials there. Next slide, please. I would like to show, go to, okay. This is one of the, comparative processing approaches for petroleum, biomass to chemicals and liquid hydrocarbon transportation fuels there. I given two examples. One is the petroleum hydrocarbons, you get it, and then you go for cracking and you make gasoline, jet fuels, which is now currently made it. The left side is entirely petroleum sector, which are now practicing entire country, and the right hand side is biorefinery, starting from cellulosic material, platform molecules, and then you get into hydrolysis, and then you can make these kind of chemicals. This left side is petroleum, and right side is biomass. And right now, 80% of the chemicals we produce in this country through petroleum sector. And the future is, I would call it, the biomass using all cellulosic material through which is available in the country, and to make chemicals out of that system. Next slide, please. I think one of the important application came in the recent history is to biofuel powered biodiesel. The first biodiesel powered flight took place from SpiceJet. This SpiceJet is now using around 25% bio jet fuel. Basically, it's from glycerol, transesterification, glycerol to you make jet oil, which is non-edible oil, can be transesterified with methanol. You get biodiesel plus glycerol as a byproduct. And I think in India, first time Indian Institute of Petroleum CSR lab has developed biodiesel through Jatropha oil seeds, and then the first the flight took place from India using biodiesel, and probably India becomes one of the few countries which are using biofuel for flying planes there. And India's first ever biojet flight took place two years back. The next one. And similarly, in Karnataka government has introduced first biodiesel plant, buses now. They used basically to make biodiesel through Jatropha non-edible oil. And nowadays, several buses are using about 25% of biodiesel to run the plant there. And this biodiesel plant, the emission of carbon dioxide are very less compared to the diesel one, because through bioread, and they are going to be more useful. And many countries now adopted 100% biodiesel, especially in countries like Brazil and all those things there. I think this is one of the important applications in the area of fuels, using biomass to biodiesel, and they are running the commercial vehicles in India. Next one. So now the question is how we make biodiesel. Biodiesel is basically synthesized from triglycerides from transesterification reaction. These triglycerides comes from non-edible oils or cooking oil, and you can synthesize using methanol, and then you get glycerol as a byproduct. And the rapidly increasing production of biodiesel has made glycerol an inexpensive byproduct. To improve the economics of the biodiesel synthesis, glycerol is converted into value-added products. Now, if you make 100 kg biodiesel synthesis, you get bioglycerol, 10% glycerol, and next will be biodiesel. So once after using this thing, what to make use of glycerol, which is available plenty. Currently, they are using for basically making some soaps and detergents, but now that cannot be used in order to make better economics or making biodiesel, and also the addition of glycerol, which is coming a byproduct, can be also converted to value products. So we thought, let us focus how we can make glycerol, triglycerol plus alcohol. You make a catalyst to get biodiesel, that's called alkyl esters, and then you produce large number of glycerol, which is coming as a byproduct. Our whole objective is how we can use different types of catalysts to make them glycerol to value-added chemicals there. I'm going to show some of the further slides how we have used glycerol to make some value-added chemicals. Next one. This we have used the one which was synthesized earlier, sulfonic acid functionalized mesoporous materials. We have used as an acidic material, and then we have carried out condensation reaction. Glycerol plus tertiary butanol yields tertiary butyl glycerol ethers with elimination of water. These are all glycerol plus tertiary butanol left side, and then we have used a mesoporous functionalized polymer, and we have carried out the reaction. The product are shown in the the right hand slide, and you have produced tertiary butyl glycerol at the around 60 degrees centigrade using this kind of material. I mean glycerol, which is we have added value using tertiary butanol to make tertiary butyl glycerol. Next one. So after making these materials, what are the end application? Tertiary butyl TT is so-called multi-butyl glycerol ethers can be used as an additive for diesel and biodiesel formulations. And it also improves the low temperature properties of diesel, especially in some of the cold countries. We can bring down, improve the low temperature properties because of the viscosity reduction there. And these are going to be used as additive in diesel or biodiesel formulation there. Currently, water is produced as one of the byproduct there, which affects the catalyst performance there. But if we can use isobutylene instead in place of butanol, we can improve the performance of the catalyst there. Next one. Okay. These are all called, again, I give the example of mechanism, cascade reaction mechanism. We have provided tertiary butanol plus glycerol, and then it reacts on the sulfonic acid mesoporous material. Water is produced, and MTBG is produced. These are the products which are coming from the reaction mechanism of producing these materials. Next slide. This is another example of, we talked about that. Another one, you can make ketonization glycerol. You can take glycerol and make acetone, which is available plenty. Acetone is cheaper. Glycerol is also cheap. Then we can make, sol-ketol, which is also very industrially important material. And in these reactions, we have used number of catalyst, mesoporous tin oxide, mesoporous MCM type, ZSM type, beta zeolite. Glycerol conversion, very high selectivity to 98% to sol-ketol. So this is very important chemical, and we have been able to achieve very high selectivity under those conditions there. And it can be one of the potential catalyst system for making sol-cat in a large pilot scale or even necessary for commercial scale. This is another example. The tin oxide was heated at a different temperature, and the tin oxide at 350 degrees centigrade heated gives the maximum conversion and also very high selectivity. Glycerol conversion increases and then it decreases there. And the best temperature, probably tin oxide to 350, was mainly attributed to the presence of greater amount of acetic sites compared to other catalysts. This is to make sol-ketol through mesoporous tin oxide. Next one.
Sir, sorry to interrupt. We may have only 2 minutes or 3 minutes.
I'm coming. Okay, I'll come in 2 minutes. Okay, last one. Next. This is another example of cyclohexane epoxidation, where again we have shown mesoporous tin oxide is a petrometyl cyclohexane to hydrogen peroxide cyclohexane oxide. Next one. This is another small example of biomass which is available. We can take glycerol as one of the product, and ammonia. Ammonia, which comes from, we can make urea. From glycerol to urea, you can make glycerol carbonate, and is also found to be very useful chemical. Urea is available, and glycerol you can take it to make glycerol carbonate. Very mild conditions you can synthesize this material, and you also get glycerol as one of the byproducts. Next one. These are our various applications. Make you anything we make it, we make some useful application, and it has got a lot of glycerol carbonate, has got a lot of application as a polar solvent, curing agents, and plasticizers and liquid membrane, and they are all used for varieties of application. So this is when the end use application, how we can make glycerol carbonate to useful chemical. Next one. This is another applications to make furfural and furfural alcohol. Next one. This is I have shown again biomass, biodiesel, and then the sulfonic acid. You can make tertiary butyl glycerols, which are of importance. Another example of mesoporous polymer material is another is ketone material, which you have used number of them, K10, ZSM5, beta zeolite, and found to be very active material for sol ketol synthesis using glycerol. Next one. This is a summary of glycerol conversion using acetone and zeolite and SVA type of materials used for glycerol destined for transacidification. Next one. This is a selective conformation of furfural to alcohol. Furfural is a very interesting material. Currently in India, we are producing through rice husk. In Andhra Pradesh, in Karnataka, and many places, you produce a lot of rice husk. Rice husk are now people burning, they are not utilizing properly. But if you take rice husk and you can go for sulfuric acid hydrolysis, you get furfural. Furfural is very chemical, and from furfural you can make furfural alcohol, which is used very extensively in chemicals and in the refining process. Furfural is maximum used there. And once you get furfural and furfural alcohol, you have a host of chemicals you can make out of these raw materials through bio route. Rice, which is available plenty, we can convert that. So in this way, my concluding remarks will be, in 20th and early 21st century, development countries were designed around crude oil due to high availability and low prices. But today's scenario based on crude oil is unsustainable over the long term. The conversion of wood-based biomass to energy and chemicals as an alternative attractive route, since the raw material is available in plenty and is cheaper rate. Wood-based biomass contains cellulose, heavy cellulose, lignin, and all this can be converted into energy and suitable treatment. Heterogeneous solid catalysts play a major role in gasification, acid hydrolysis, cracking steps in biomass conversion. So far, the drawbacks of reported catalysts are low thermal stability, but you can improve the activity and the recyclability. Hydrothermal stable zeolites or carbon-based catalysts may be future for hydrolysis of and cracking of biomass. So this is current stated, and in our institute, Pune Institute of Scientific Research, we have been focusing very aggressively on biomass to chemicals, and a group of my colleagues led by Dr. Shanbag and Dr. Sanjeev and his students have been actively working on how to convert biomass into various chemicals and how we can say the foreign exchange to this country and how to develop some new materials in this scenario, and that I try to integrate their work in my talk there. So I would like to thank for all of you for patient hearing, and I also thank my colleagues who helped me to make this work, and also Dr. Naveen and the authorities of Amrita University for giving me the opportunity to share some of the work that we are doing in our institute. Thank you very much.
Thank you very much, Professor Halgari, for giving us a glimpse of what your institute is doing in the conversion of this biomass into the value-added products. So with this, I see we are actually late by 20 minutes, but maybe we can take one question. So anybody has a question, please raise your hand. Okay, I see somebody's typing. Okay, so there is a question. I'll read this for you. Meso SNO2 bifunctional. ZnSN is biodegradable. They're asking about this zinc tin.
No, it cannot be biodegradable because tin oxide is heated around 350 centigrade, and it has got some bifunctional sites on the catalyst surface, and those sites are responsible for conversion to biomass actually. But they are not degradable.
How to recover if it is used as a catalyst?
I think after the reaction, you can recycle it. You can take out the tin oxide, again activate it, then reuse the same reactions. Actually, you can convert 4 or 5 times. You can use and then recycle it.
Okay, sir. I think with this,
okay.
Yeah.
Thank you.
All, let's thank Professor Halgeri for his time and for his presentation. So we'll move to the next talk. We have Dr. Maya Matthew from CSIR Pretoria. I saw she's here.
Hello, Dr. Naveen.
Yes, Dr. Maya. Yeah. So yeah, she's on the board. Okay, so I request Dr. Sridhar to give a brief introduction about Dr. Maya.
Naveen, can you hear me?
Yes, sir. Loud and clear.
Good afternoon. It is my honor introducing the next speaker of the day, Dr. Maya Jacob John. Dr. Maya holds a master's degree and a PhD in chemistry received from Mahatma Gandhi University, Kottayam, Kerala, India in the year 1998 and 2006 respectively. Dr. Maya joined CSIR South Africa in the year 2006 as a postdoctoral fellow and was later absorbed by CSIR South Africa, appointed as senior researcher in the CSIR Polymers and Composites Research Group. Dr. Maya's current position is a principal researcher, CSIR South Africa. Also, Dr. Maya is a research associate at the Nelson Mandela Metropolitan University in Port Elizabeth, South Africa. Coming to the research field, the main focus of Dr. Maya is the development of bio-based composites and their applications. Dr. Maya's current research focus is the development of materials from renewable and sustainable resources. Dr. Maya holds a patent and is the editor of a book published by the Royal Society of Chemistry. In a short span of time, Dr. Maya could add to her credit more than 100 publications, including publications in international journals with high impact factor and book chapters. The total number of citations to her credit is nearly 8,000, with her articles being in the Science Direct list of top 25 articles in journals. On behalf of Amrita Vishwavidyapitham, on behalf of ICMS 2020, and on behalf of myself, I invite Dr. Maya Jacob John for delivering her speech on bio-based composite materials for a circular economy. Over to Dr. Maya. Thank you.
Thank you for the kind introduction. Dr. Naveen, I just want to know if you can see my slides.
Yes, Dr. Maya, you can see.
All right, then morning to all. The topic of my talk is bio-based composite materials for a circular economy. I'm going to begin with an overview of the CSIR and then speak about my research group and what our research focus areas are. And then we'll go on to the projects in 2 thematic areas. One is natural fiber composites and the other one is biomass conversion to composite products. And then we'll wind it up with by mentioning our collaborating partners and acknowledging our funding agencies. So this is the CSIR, and we have presence in different parts of South Africa. The main office is in Pretoria, which is the capital, but we have regional offices in Port Elizabeth, Durban, Cape Town, and Johannesburg. Our vision is to be accelerators of socio-economic prosperity through innovative R&D and We do this by collaborating with universities and industries via short-term and long-term research projects and by transferring technologies to the market. So these are our CSIR values. It's excellence. We believe in excellent R&D and science and translating the science into tangible products for the industry as well as for the common people. We are all about people. We are people-centered and we cherish the rich diversity and culture that the people bring to us. We believe in honest and fair dealings, and we are honest and fair with each other and with our external clients. We are also into collaboration amongst the different clusters in our group, as well as collaborating with external clients. So we are one of the best and we believe in collaborating with the best. So this is our chemicals cluster and it has two wings. There's a biomanufacturing technology and there's a Center for Nanostructure and Advanced Materials. The Center for Nanostructures and Advanced Materials has 7 research groups, and I'm from the Advanced Polymers and Composites Research Group. So these are the focus areas of the research group. The first one is waste valorization and conversion to value-added bio-based products. So by waste, we mean industrial and agricultural waste, and converting, the first step would be fractionating the waste into different components like cellulose, hemicellulose, and lignin, and converting it into value-added products. Our second area is the development of bio-based materials, and these include biocomposites, like natural fiber composites, blends, and these can be biopolymer blends, bio-nanocomposites, which are cellulose nanoviscose reinforced biopolymers, and these are mainly developed for either replacement of petroleum-derived products, and this will fall into the category of single-use, replacing single-use plastics, or we would impart additional functionality to these materials, like improved flame resistance and water resistance, so that these can be used in advanced industrial sectors like the automotive and the aerospace sector. And our third focus area is that of recycling and end-of-life studies of bio-based materials. So we work on developing materials from plastic waste. So it can be e-waste, which is electronic waste, and developing new formulations and new composite products from recycled materials. And we are also equipped with a biodegradation testing facility. So here we can study the biodegradation profiles of biodegradable materials and establish the profiles in different media, like soil, compost, and water. And it is also we are also capable of studying the emission of carbon dioxide from these materials during biodegradation. So what are the key drivers that support the use of bio-based materials? One is the fluctuating cost of petroleum-derived materials, and it's also depleting at the same time. If you look at the properties of bio-based materials, the technical properties are on par, in most cases are on par with conventional plastics, and you have additional advantages of biodegradation and compostability. Now, the importance of a carbohydrate economy. For a country like South Africa, the development of a sustainable future is very much dependent on maximizing its natural resources like biomass, natural fibers, and so on. And then you also have certain drivers like environmental legislations and bio-based incentives, which is driving or pushing this move towards the use of bio-based materials. So in different sectors, you have different legislations. For example, in the aerospace sector, you have REACH and Clean Sky. Now, Clean Sky is a program that is aimed at greening of aircrafts and reducing pollution, while REACH, as you would know, when it is implemented, it would ban a number of plastics and chemicals, and then one would have to come up with viable alternatives, viable environmentally friendly alternatives. In the automotive sector, there are different directives, like the end-of-life vehicle directive, which is stipulating that 95% of automotive components should be recyclable. For the manufacturers of cars, there's the fuel economy standards, which is now I think is sitting at 22.5 kilometers per liter. So that is all pushing the drive towards lightweight materials, as well as greener materials for automotives. In the packaging sector, there are regulations like ban on single-use plastics. In the African continent, about 14 countries have banned single-use plastics. So one needs to have viable alternatives, really. And also, there is also the stress on reducing carbon footprint of packaging materials. So earlier we had a very linear economy, which was you manufacture a material, use it and dispose of it. But now we are moving into a circular economy where a material is manufactured, used, and it is retained in the economy. And there are three key points to a circular economy. One is minimizing the natural resource utilization and pollution emission, minimize waste. Waste is now no longer considered as a waste, but it is a feedstock from which valuable materials can be derived. And the third key point is promotion of recycling. So hence, bio-based materials or plastics, it's aligned to the principles of circular economy. So this is our research group focus. In a nutshell, it represents our group focus. And we start with a bio-based material, and then we move on to the designing of unique bio-based material formulations. And if there is a requirement for modification, we do that so that the product can comply with technical requirements, and then it is converted into a prototype for the different application sectors. Now, this is very much in line with the new plastics economy vision, which talks about eliminating all the plastics that we don't need and innovating to ensure that the plastics we do need and use are reusable, recyclable, or compostable, and also to ensure that we circulate all the plastics that we use so that we keep them in the economy and it does not end up in the environment as an eyesore. Okay, we'll just move on to our R&D and natural fiber composites. So if you look at the history of natural fiber reinforced composites, you'll see that it all began in the aerospace sector with the introduction of Gordon Airlight, which was a flax phenolic resin laminate, which was used in the fuselage of planes. Now, why is there this interest in, or what are the attractive properties of natural fibers? One is its high specific strength. It's comparable to glass fibers, low cost. When natural fibers are reinforced or incorporated in thermoplastic, there is weight reduction up to 30%. Natural fibers are biodegradable and renewable, so that creates a positive environmental impact. When compared to the synthetic glass fibers, natural fibers are non-abrasive and non-hazardous. And finally, there is the worldwide availability as well. Some of the issues with natural fibers is concerns over fiber quality and consistency. Natural fibers are composed of cellulose, and because of the hydroxyl groups, they are hydrophilic in nature. So sometimes there is bonding problems when you use a hydrophobic polymer matrix like polypropylene. Natural fibers undergo degradation at temperatures higher than 200 degrees Celsius. So you will have processing problems with high temperature plastics. So this is just to show that natural fibers are composed of cellulose, and you can see the hydroxyl groups, and that's why they are hydrophilic. The other components are hemicellulose, which is a mixture of several sugars. You have lignin, which is an aromatic complex macromolecule comprising of phenolic moieties, and then there's pectins as well. Now, earlier I mentioned that because of the hydrophilic nature, there is bonding problems if you are using a hydrophobic matrix. So in those cases, it is quite imperative that you need to chemically modify the natural fiber. And some of the common modification techniques are mercerization, which is the simple alkali treatment, acetylation, which is treatment by acetyl chloride, and usually acetyl chloride treated or acetylated natural fibers exhibit best water resistant properties. Selenization is use of silane coupling agents, and they act as bridges between the fibers and the matrix. And then you have isocyanation and grafting by the use of the common chemical agent malic anhydride grafted polyprop or polyethylene. Some of the limitations of these chemical methods are that the hydroxyl groups are tightly bound, and sometimes the extreme modifications can disrupt the structure and may result in impaired properties. The other issue is that most of the chemical agents are synthetic and toxic in nature, and that can affect the biodegradability and renewable nature of natural fibers. So it is ideal that one uses or one tries to use environmentally friendly plant-based coupling agents. And some of the studies include the use of furfuryl alcohol, the use of fungi, and in one of our studies, we have used zine, which is a protein that is obtained as a byproduct in the milling of maize. And zine is actually an amphiphilic coupling agent, and it also forms linkages between the hydrophilic natural fiber and the hydrophobic matrix. So these are the applications of natural fiber composites, and you can see it's mostly in the automotive and in the